resistivity, as we talked about this morning. They could use a surface time domain EM in a Turan configuration or in a sling ring configuration. Then they go ahead and they work with all of these. They do a test over the deposit that they know is there. They decide that, okay, we're going to go for this Turan, and then they use that. They also do some borehole work, and they find some awful targets. So it's kind of a nice story, and the reason I like it is that just the way it's all laid out, like this is really responsible use of geophysics. We got reconnaissance, you find something, do a little bit of groundwork to help delineate it, have a couple of possibilities for time domain, EM or ERT, which should I use? So to test that, pick the deposit area that you know there's something there, and see which one works best there, and then you're going to use that for the rest of the area, and continue on, and then gradually do some surface to borehole work, get some idea about what's there on the target, and then you also see a couple of things that are just kind of interesting, sort of off-hole. Actually, the miscible mass is interesting because you did the DC resistivity this morning. Right? So miscible mass, for people who are unfamiliar with it, so it's basically DC resistivity, but you're putting an A electrode. So suppose you got a conductor here, right? So you got a hole through there. You just put your one current electrode in here, and the other one way out there. Okay? So that's all it is. But that's great. So now you know exactly what's going to happen, right? The moment that you put that electrode in here, this whole thing just shines up, right? There's going to be positive charges everywhere, and those positive charges are going to give rise to potentials. So, okay. Yeah, and it turns out that the ERT didn't really work very well. There's EM systems were okay, and there was one kind of borehole or sort of surface to borehole, and it looked like there was this off-hole conductor, and so then they extended it and found something like that. So there is your conductor. Yeah. So it's just kind of a nice. It's a nice case history just because it shows all of these different aspects. And you've got, as I say, the initial V10, the miscible mass, you've got these Brown tests, and then you've got a Turan survey where you basically have a loop, and then you measure both surface data and also measure ground data. So that's my data. Yeah, as I said, I'm happy to talk more about that tomorrow, but it's pretty easy case history. And that was actually written up in it was either a leading edge or a first grade article. So what I'd like to do now is we'll continue with inductive sources, and we're going to look at frequency domain.
Doug, do you mind if I just jump in and get your video? Okay.
Oh, yeah. This is serious. Yeah. We're still. Oh. Okay, so we're still going to use a vertical magnetic dipole. We're going to look at the effects of frequency and do a case history with groundwater. And you're already, I think, pretty prepped here for this. It's what you kind of might expect to see. So we've got, there's no difference. Time domain, frequency domain, kind of shape the responses are doing, but everything else is the same. So here's now what happens for our background half space. 100 meters, and here's our current density. So now they're going to be circular in cross section. They're going to, these are the absolute values, so the high magnitudes here, and not very much current directly beneath the loop. So currents are kind of going out like this, and then they're going down. So there's sort of a null directly beneath the transmitter. And that's your BZ field, but again, we're trying to measure something up there. And then if you look at the effects of frequency, a pretty high frequency, 100 kilohertz, here's the currents, and here's the magnetic fields. You can see the magnetic fields actually kind of complicated. What we're seeing out here, measure that. And at a lower frequency, things start to diffuse down and upward. Same as time. So here we are with a high frequency, low frequency, and again, the point is at really high frequency, you're kind of confined right up there. Lower frequency here. These plots are not as extensive as the time domain. First of all, because I don't think they need to be. But secondly, this fact that things go from the the real into the imaginary and back again actually makes it kind of challenging to see, okay, what should we plot and how to portray it, which is why it's much nicer to present physics in the time domain. So now if we have a layered Earth, so we're going to put in a resistive layer and then also a conductive layer. So you're already completely prepped. You're pretty sure you're going to know what's happening. Here's your current density. So this is the Y component. It's forward, so now we got click in, out. And if we just have everything is 500 or 100 ohm meters, we just get something that looks like this. Oh, sorry, that was 100 meters. Now we make it resistive, so we don't see any manifestations, particularly in there at all. If we make a conductive layer, then we see something in the top and also see something in the conductive layer. And if it's very conductive, then most of the stuff is up here. So exactly just the same as in the time domain. The resistive layer doesn't affect things very much, but we do see the conductive layers. And if we look at magnetic fields, yeah, they get complicated, but we're up here, and the important thing has to do with sounding curves. So here is this is the real, that's the imaginary, and frequency from 100 to 100,000. If you put in that resistive layer, there's no change, not really. So that's with the resistive layer, the dashed, and solid is without. But if you put in a conductive layer, you can see the difference between solids and dashes, and it's very conductive. It's usually. So our shielding problem. Now we know, right? This is the guy who hooked us for the DC resistivity. Remember, for the DC resistivity, we were fine without it. Put it in, and all the current gets channeled above. The top of that is at 7 meters. All of the current is above 7 meters. Nothing is penetrating in through that. So you just see that resistive layer. And now if we put in this guy here, so here is here's the current without any resistive layer. Put the resistive layer in, there's really no change. So it's transparent. And so with the a resistive layer, then basically we're completely transparent. So you're good to go. Put your deposit beneath the resistive layer. Use an inductive source, you're okay. Use the galvanic source, you're pooped. And the question then is what happens with a conductive layer? See anybody? What's going to happen? Put a conductive layer in?
It's going to go on the conductive last time with the time.
Okay, so yeah, so when we do DC resistivity, yeah, it just got channeled around. Remember, so this was DC resistivity with the conductive layer, and then just got channeled straight across and then back up. Right? So we were blind to this. So what's going to happen? Pardon?
I'm not going to probably see the loss.
We're not going to see very much because this is a conductive layer, right? So it's going to absorb all the energy, and this is without that conductive layer. Now we put that in, and so before we were able to see the sphere. Now basically we're just getting masked by that conductive layer, so we're really pretty insensitive to what's going on.
Will you see that in really, really late times?
Will
you start resolving it in really late times, or will it just signal to noise emitters?
Well, that's a hard question. It kind of depends what your noise is. I mean, you know, given that if you have an infinite conductor, it's not going to go through. But you've got a finite conductor, it's a finite. And actually, the thing that's important is sort of the conductivity thickness product, something called a conductance. And at some point, late enough in time, you might actually get through that and see something. But the amplitude of that could be really small.
That's the other thing with an EM system. The magnetic flux lines are still going to be going through that body, through that layer, and impinging on the body, aren't they? So your magnetic flux lines, you're reducing the field, it's getting terminated, it's still going down into that body. And still exciting, isn't it? Even though you can't see the response through it.
Yes, but the magnitude of those, I mean, sure, the direction of the flux line goes through, but the amplitude of those magnetic fields, I mean, they just are decaying markedly as they go through that layer. So at some point, yeah, you're technically, with an nth digital computer, you're going to actually see some kind of response, but it's just simply not big enough to really observe.
Hence the need for high-power transmitters as well.
Pardon me?
Hence the need for high-power transmitters.
Exactly, yeah.
And low transmit frequencies to get through conductors.
That's right. So you want to, you need to have a low frequency so that you've got a large skin depth, and yeah, you need power to get through. So that combination is always the ticket to. Good. Okay, so let's do one case history for groundwater. So this is in your home turf here. We actually, on our trip from Adelaide to here, we were so excited because we thought, we should go over the Murray River. So we talked to the flight attendant and we said, where's the Murray River, right? And she says, we're going to see that 15 minutes after takeoff. So we sit down in our seats, and we're down there about 10 minutes, and then the captain comes on, and he says, for all those passengers interested in seeing the Murray River, it's on your left. We actually have a picture of the Murray River. Okay. It's the little things in life. Actually, it kind of looks like that, right? It's just sort of meanders around. It really does meander. Yeah. So this is an area of kind of ecological sensitivity. It happens right down here. And the basic problem is that you've got this irrigation area up top, so it's sort of a highland irrigation, and all these fertilizers and salts eventually kind of meander down through, and then they get, well, they do two things. First of all, they salinize this region in the floodplain, which then damages all of the ecology, and also it gets into the river itself so that the river becomes a transportation of the salts. So what they were trying to do is to really kind of understand what was going on here. Here's an example of what the area looked like with all of that salt. I mean, just kind of completely devastated the all of the vegetation. So if you just have a river and you've got this stuff that's coming down saline water, as I said, it comes through the floodplain and into the river. So it was just causing a lot of ecological damage as well as increasing the salinity of the river. So then they thought about a couple of things. One is that let's see what we can do for actively working with this. And so they've got saline water coming in here, and then perhaps they could just withdraw water from here. So they withdraw saline water from there. So there's sort of a borehole here, and then they pump it back up into some kind of pond up here, and then let it evaporate. But effectively, you're trying to haul out saline water from here and get rid of the salts up here. So that was a plan to try to do that. But at the same time, they wanted to see what they could do from the point of view of injecting fresh water. And the idea there was to take a strip along here, inject fresh water, and then see what the result would be. And here was a situation in January 2006. This is the conductivity. It's micro Siemens per centimeter, kind of a strange unit. But anyway, blue is resistant, red is conductive. So this is sort of fresh water here, salt water over here. In January 2006, the situation looked like this, but then they pumped fresh water in and were able to get a conductivity structure that looked like this. So it's definitely proceeding inland here. So actually, yeah. But anyway, that was kind of the goal. It was sort of a little bit active, and at the same time, they were trying to find out a few more things about what's happening globally, because it's just like it's impractical to drill and sample the entire floodplain, and they could at least kind of find out what the state of salinization was at a particular area. Then, they might be good to go. So the physical properties, of course, are basically controlled by fresh water and salt water. So fresh water is low, like 100 ohm meters. I'm not sure what we came up with for fresh water here, but anyway, that was a low value. And then salt water, 100 times greater than that. So they've got this transect in here that I showed you earlier, and that's what they're now going to look for, is studying this transition between high conductivity and low. So the survey that they chose, well, actually they did both SkyTem, so they both did a time domain and a frequency domain. We looked at both of these. What I'm going to show you here is the frequency domain system, the Resolve, that was done in 2008. So this is one of those horizontal coplanar systems. So here's the bird got coplanar coils that are separated by a particular distance. And there's about 5 frequencies from 400 to 130,000. There's also some vertical coaxial, so VCA, so vertical coils, coaxial, get a name, like that. So we're just going to look at the coplanar results. And the resolve are in the green, so yeah, forgot what the line spacing was, but I think it's around 100 meters or something like that. So here's a picture, and I like showing this picture at this point in the game because it's one of those opportunities for everybody who's here to personally recalibrate like what they know and what they don't know. In other words, what I'm trying to get at is if I had shown you this picture the very first day, 10 after 8 in the morning, and I said, okay, here it is. Got real, imaginary, different frequencies. Got response curve, sounding curve. You could ask yourself, okay, what would that have meant to you? What information would you have gleaned from that at 10 minutes after 8 this morning compared to 37 minutes after 1 in the afternoon? Okay, so here's some of the things that I think should be kind of self-evident at this point. So first of all, we got frequency, 382, 36,000. So which frequency is going to be more representative of the near surface? Yeah, so the higher frequencies. So this is whatever is happening in this picture. It's a little bit more representative of what's going on at a higher region near the surface compared to this. Okay. Secondly, I got a real and imaginary part. Okay. Maybe a lot of people knew, but now you've got it. I mean, you see, oh yeah, right. So there's my response signal. It's got sinusoid. It's got an in phase, quadrature phase compared to my primary, and so I'm going to have a real and imaginary response. The other thing is that you look at this sounding curve, and it's like, okay, what's that? So here's frequency along here, and here's our response, the secondary over the primary. And we got something that's looking like that. So as a function of frequency, we got this kind of a shape. But that is, of course, exactly what we see here. Here's our response curve, remember? And when I'm looking at this kind of a curve here, I'm seeing the real part increase and the imaginary part going like this. So what does that mean for the induction number? Are we at a high induction number or a low induction number? We're at high, right? So we're in this part of the region up here, right? So the real part's up here, and the imaginary part's going up. And I see a magnitude of response that's really high here, the reds, and low here. Now I know that my magnitude of the response is going to depend upon my electrical conductivity, right? So I just look at this map, and I'm seeing that, okay, I've got some more conductive regions probably up here than down here, right? So you're prepped, right? And this is where I think we should all try to be. If we look at a map of data, we're not necessarily going to see geology, but we got stuff that we can grab onto that, like, okay, I kind of get that. I sort of understand that. Okay, so there's our data. That's the information that you gleaned. And I said, do a calibration check on yourself personally. Decide, okay, what do you see in this curve now compared to what you did 4 hours ago? And hopefully, there's some. So for processing data, do a stitched 1D inversion. And for examples like this, that's probably pretty good. We've done this in 1D and in 3D. And there are places where things are kind of changing pretty rapidly that the 3D actually makes a difference, and there's more stuff there. But first pass through, stitched 1D actually kind of works pretty good. So this is the conductivity at 8.6 meters depth, and again, kind of almost looks like the data, but it's now calibrated into true conductivities, and you can see that this is more conductive than this region right here. So the interpretation, so we got the region of higher elevation here, and there's stuff that's coming down. The interpretation is that this whole part of the region back here is actually kind of gaining salt. It's there's salt that's sort of inflowing, whereas in some of the regions out here, there's actually fresh water that seems to be going into that direction. Informative, and it's even more informative when you put this within the context of time lapse. So GA or CSIRO, one or the other, or both, have also funded a 2015 survey. So we have data from 2006, 2008, and then there's one from 2015, and there's market differences. So that's kind of the synthesis. We've got this sort of background model. There's stuff coming in, and with an airborne EM survey, you can get some sense about which parts are heavily salinized, and maybe some idea about where the fresh water is going into the region around and where it's not. I'll show you this. It's very short. So we were in Tokyo not so long ago, and geophysical institutes, they're geophysicists. They want to solve problems, and so there's the Advanced Institute for Geophysics in Tokyo, and a good friend of mine, Yuji Hata, is there. He's actually heading that group, and so we were talking to him about some of the things that that they're doing. He showed two things. One is this. This is the front cover of their brochure. So this is their advertisement to the world, if you like. Okay, here's our big institute, and this was on their front page. And I just so resonated with this. I thought, oh, we got to show this. So first of all, there's seafloor EM, which is now very big for Japan, especially gas hydrates or methane hydrates is big. Seafloor massive sulfide, submarine massive sulfides is big, as well as the usual hydrocarbon de-risking and a few other things. So seafloor EM, methane hydrates, there's oil, there's gas, aquifer storage and recovery, and also CO2 sequestration, radioactive waste deposits, issues about groundwater, seawater, sort of the ocean groundwater interface, where that guy is. Japan, lots of tectonic activity, so they've got hot springs. They have to worry about acid mine drainage. You've got mineral deposits, and you've got geothermal energy. That kind of encapsulates the discourse, and there's just a huge number of projects there. But this one was kind of interesting because, as I said, if you're a government agency and you just want to do geophysics, you also have to resonate with the people who are controlling the purses, and you need to sell them on something. So this is one of the things that they did, and there was an earthquake in Japan, and it caused a landslide, and all the stuff that came down buried a few cars, and they didn't know whether there was people in the cars or people not. Right? So they wanted to find these cars quickly, and they had no feasible way of doing it. So what they thought they would subsequently embark upon was a drone aircraft that is going to carry a frequency domain system and then quickly be able to fly over things. So that was good. I mean, it's a practical solution or a practical application and something that government people could really affiliate with, right? Because you don't want to have people buried in cars with lots of people. Fine. So here's what they have. So here's their drone. So it's sitting up here. And then here's their bird. So their bird, like it looks just like the Resolve or any of these others. It's like a coplanar guy. And so you got a transmitter and receiver. But again, just the same as with any airborne system that we have these days, you need to worry about noise from your primary carrier. That's why everything is down far below the helicopter or the aircraft. And there's a question about, okay, how far does it have to be? Do some tests. So this black line here, so this is the recorded value. So that's their signal that they're getting, not for the car, but just over background. And this is frequency on this direction. So here is, this black line is noise of 1400 parts per million when the system is 3 meters below. If it's 4 meters below, you get the red line. If it's 5 meters below, you get the blue line. So that's acceptable. So that means, okay, now I need to have this 5 meters below. This establishes the important parameter. Then you have to remember that, well, everything falls off as one of our cube, right? So the transmitter field falls off as one of our cube. You ignite something here. That falls off as one of our cubes. So you need to be as close as possible that you can. So here is the two potential vehicles, 1 at 1.5 meters, 1 at 3 meters. So they flew this. So first of all, in phase and quadrature were obtained at multiple frequencies. But it's a metallic object. Metallic objects have very high induction numbers. So most of the signal is the in-phase part, and so that's basically what they plotted. They just plotted the in-phase component. And if you look here, it's red, and that turns out to be the car that's 1.5 meters deep. And here there's a manifestation of this guy, which is the tree. But the thing about that is, like, it's all the same, right? Things are miniaturized, they do this, they do that, but the principles are identical to what we just looked at, and they will carry over to other applications too.
Now, how big is the drone?
I don't know. I think it's only like meter-ish, something. It's not very big.
How long would it take to fly that surveying process?
Oh, I have no idea. Let's see, what one's that? Did they have scales on? This is 12 meters. So these are maybe 30, 40 meter lines.
One level?
Not really sure.
Why did they choose frequency over time domain for something like that?
Pardon me?
Why frequency domain rather than time domain? Is there an easy answer?
Not from my perspective. I mean, for me, all of these really important questions with respect to instrumentation and stuff like that, I'd refer to Mal. I mean,
They seem to be using frequency domain more for shallow mapping, don't they, rather than deeper mapping.
yeah, it might be because you can actually get higher. Like you can get pretty high frequencies, maybe compared to the earlier times.
Extremely high frequency, don't they, compared to time domain?
I think if I was a weight and equipment size and anything, putting the transmitter in the time domain system compared to a battery power frequency domain system would be a hell of a lot easier to miniaturize.
And miniaturize, which
The frequency domain would be smaller, lighter, self-contained electronics and stuff. I don't know, you're putting a time domain system in something more switching and fucking miles and all the rest of it.
We could do it. I mean, we've got miniature condemning EM systems to be used for water detection work. It'd be quite possible. We actually have a drone system too.
Oh, do you have?
We do. It's not quite commercial yet. We're struggling with some navigation software, but it's a little helicopter. That's a quadcopter, a multi-rotor system. It houses like a little helicopter. So we can show you pictures of it at some stage if you're interested. So we've been flying it, doing UAV SAM, similar to the heli SAM that we're doing before, only for smaller areas. And so the idea to basically do fixed-loop EM surveys with it.
What about the magnetometer sensor? Wouldn't that function? Hang a magnetometer sensor down.
That's what I use there. In that case, it's just a mag survey. I mean, it's a mag
Any bump, stop really digging.
Sorry?
Any bump, stop digging. Because the clock is on it.
Maybe. So that's right, they could have done it in that case, yeah.
Even less.
We were approached to do the same kind of thing as that by Newmont actually.
Oh, yeah.
A landslide in the US at one stage, they're trying to do the same thing. Locate some buried vehicles,
Oh, okay.
like people killed.
We're-
We didn't get involved in it, but I mean, it's a problem that comes up every so often. And the big issue, of course, is that nobody wants to actually walk on the landslide to do any sort of ground survey. So that's where the drone was very useful, safer, of course.
There was one trying to find lost taglines down in Antarctica or something like that as well.
I have heard of that, yeah, that's right.
Sorry, you lost what?
Snow vehicle taglines
Oh, okay.
In Antarctica a few years ago, but they didn't know where they were.
So that's.
Just trying to see where stuff
Yeah, so the real art, I think, comes into actually implementing these things. How do you actually make it? How do you get the noise now? So it's, at some level you can kind of understand, the basics of, of what the instrument is going to be like, how things are going to likely to work, but it's always in getting that extra power, getting the extra reduction in the noise. That's the thing that distinguishes one system. Okay, so the next stop is kind of like an integration. So we're going to go to grounded sources. So I'm going to talk about the basics. I've got a case history for the Deccan traps. We've got quite a bit of other stuff here. I'm not sure whether we'll get to it today or whether you're interested. But there is one thing that's a DC EM inversion, which might be of interest to people here. We've got a lot of stuff on marine CSEM cases. We've got a kind of a tutorial and case history of methane hydrate. So this is a very rich kind of area. And our motivational examples, are the seafloor EM, oil, gas, volcanoes, minerals, and in particular, we're going to concentrate on, ground-based surveys that, collect data either in the air or on the ground. And here's why this is kind of integrative, and it's also why the material was presented in exactly the way that we chose to do it. Because we started off with DC resistivity, currents, all this talk about charges, right? And then we talked about inductive sources. There's no charges that are kind of built up in here, at least if you have a completely fine conductor and very resistive medium. It's just currents. But now what we're going to do is we're going to take this DC resistivity, so we've got this big long line, And we're going to put through a time varying current. So it either could be transient pulse off, or it could be a harmonic current. Either way, we're going to get induction as well as galvanic currents. So we're going to kind of parse that out. We can get some idea about what's going on by just looking at an electric dipole in whole phase. So electric dipole is just a little piece of wire, little generator attached to it, and two prongs are sitting in a homogeneous space. And yeah, it's a dipole, so things are going to decay as one are cubed. And we're going to look to see what happens with this guy as a function of time. So let's do this. So here was our system, the current's on, we turn it off, and now we're going to watch what happens as a function of time. So you're asking about diffusion distance. Here's the complete formula. Take the mu, the 2 out, and then we got the units properly. So at 10 to the minus 4 milliseconds, which is a tenth of a microsecond, the currents now look like this, and our diffusion distance is only 4 meters, so that's 80. A bit later, 13 meters. Later, it's like this. So you can see what's happening as time goes on. These currents are going to decay in amplitude and just spread outward. The color schemes will stay yellow, but this is 10 to the minus 4, or 0.4. This is 10 to the minus 4.4. That's 10 to the minus 5.6. So things are really decaying. 10 to the minus 7.1. But you get the idea, and now you're expecting this, right? Put a current in, and it's just going to decay away, diffuse outward, and you can see how the amplitude continues to go down and how everything just kind of spreads out. Frequency domain, nothing really particularly different. In the frequency domain, the primary is always on, but the data are partitioned into real and imaginary. And if we look at what's happening in the frequency domain versus the time, so here at time 10 to the minus 4 milliseconds, if you're trying to translate what's happening in frequency from your intuition of time, just take the time, make reciprocal, and there's your frequency. So 10 to the minus 4 milliseconds, 1 over that is 10 to the 4th kilohertz. So if we kind of look at what the currents are like, you see, okay, that's pretty much the same. And we have a skim depth, and we have a diffusion distance. If we look later at lower frequencies, it's something like that. A little bit later, get something like that. Later, like that. So, same. So this is this is essentially what happens. Whether it's time or frequency, if you have early time or high frequency, kind of get something that looks like this. At later time or low frequency, everything has kind of decayed away, and it's mushed, and these amplitudes are very different in scale. Okay. So that's what happens in a whole space. Now let's again make things just a little bit more interesting. Let's look to see what's going to happen in a half space and try to see if we can kind of figure out what's going on. So we're going to have an extended line source. So it could be just something that looks like this. So we've got an A electrode and a B electrode, or we could make it into a horseshoe. Either are common. And we're going to put this on the surface of the Earth, and then we're going to try to see if we can't detect a body. Again, there's the usual questions about geometry, frequency of time, which variables, da 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 da. So it's a lot to do, but we can gain a lot of insight just by looking at a very, very simple problem. Let's do that. Let's look at this guy. So this is a grounded source. It's got the A electrode here, B electrode here. At steady state, we know exactly what happens, right? So we've got currents in there. So here's our circuit, got our generator here. So we can look at something just before shutoff and then something just after shutoff. There's a couple of parts in this picture. There's a wire, and there's also currents in the ground. Let's just take them one by one. Let's take the wire. So suppose I've got a current in a wire, and then turn it off. What's going to happen?
You produce an EM response in the ground.
Magnetic field.
Pardon me?
Magnetic field occurs.
Okay, so electromagnetic response. Can we be a bit more explicit?
As you circular magnetic field, when the current is on and when you stop, there'll be reverse.
Okay. So what about currents? What's going to happen? What are the currents going to look like?
I guess it'll flow along the path that used to flow through the ground, but from the ends it'll try to reverse back through a deeper path.
Try that again?
Does it?
The ground part of the current could be about similar, but from the ends of that, it can't go back through the wire, and we'll try to get back through the ground further out and deeper down. As it tries to reduce the speed of the magnetic field decays.
Okay.
It'll induce current flow in the opposite direction back to the transmitted current.
So we'll kind of induce a current in the other direction.
Does it?
And there's lots of possibilities. Anybody else? I see lots of fingers going.
Magnetic field would be after when you turn off the intensity of magnetic field is maximum, but it will decay.
Granted, it'll decay. What's it going to look like just right
You
after?
get a curling electric field around any changing magnetic field. So if your main field at T naught is going around the wire, every time that sort of decays away. At every point you get a curling electric field around it. So you sort of get the sums of those. I don't know.
Those
so
symbols
like
goes
sheets.
like
But certain current sheets? Or?
Yeah, I don't know.
It's complicated because you have a rapidly switched off current in the ground as well as in the wire, of course. So.
Right. Yes, but let's just take it one at a time. Right. So again, if you're trying to understand anything, break it down into the simplest parts. Understand each of the parts, and then put it back in.
It's not supposed to be like. Did you say sauce before? Are you told us?
No, this one. No.
Oh, that maybe it's like those smoke.
Oh, like smoke rings? Yeah. So the smoke rings are kind of a diffusion thing when things are going out. So that you've got currents that are, once the currents are established, then they kind of diffuse outward.
Yeah.
But we're going to look before We're gonna look before the smoke rings have a chance to smoke, right?
Right.
Is the loop effectively, rather than being, if you just a normal EM loop, is it effectively with your electrodes, you're creating a loop in that direction rather than that, so therefore your mag field's going to be horizontal rather than vertical?
Depends where your wire is. Depends whether the
I suppose
wires
so,
and the
yeah.
electrodes are out in a horseshoe shape, doesn't it?
Yeah. But you're using the ground to complete the loop though as well.
Yeah, that's right. Don't tell us, don't.
Anybody else?
Are you gonna get the current flux going out of the ground like that? Like the lightning rule?
But wait, could the current go out of the ground?
Well, the field.
Or the magnetic field?
Yeah. So right, the current's like that, you've turned it off, but the magnetic field's coming out of the ground. Is that right?
Well, the magnetic field from the wires is clearly searching.
Yes.
I'm searching that wrong. Okay, so there's a statement that's often made in electromagnetic induction that says the surrounding Earth, the surrounding material, does not like to have a change in the magnetic field. That's effectively what Faraday's law was with Lenz's law, right? So that the moment that you turn a current off, okay, the region around you does not want to see any change in the magnetic field. So there is going to be a current that is going to be set up to make sure that the magnetic field doesn't change. Okay, so with that statement, now tell me what the current is. Perfect. Okay, so you're going to get a current, but now we can also question which way that current is going.
Opposite the whatever it
Other
wants
way.
to give the opposite the B, right?
So you
So if
agree
it's
with
going this
Mal, it's going to go the other way.
Yeah. Well, that's one thing.
That's this side of it. That's this side of it. Okay.
Uh-oh.
Yeah, this way. If it's going that way at the beginning and you want to compensate for the change, so I have to go the other way around?
Yeah, but if imagine I'm sitting out here, right? Like, at one moment the current's coming this way, I've got a magnetic field. This, right? And the next moment, it's still supposed to be the same because I haven't felt any different.
Right.
Yes.
Okay, I'm gonna know.
Yeah.
Change your session.
Okay, so
I'm so confused.
this is simple.
No,
right?
it
This is
has to
fun.
go that way. He said that, I stick to it.
Yeah, we'll always listen to Mel because I don't think I've ever heard him wrong. So he's going to go this way. Except this might be a first. Okay, so the moment I turn that current off, okay, there's an instantaneous reaction in the Earth to protect these change in time-varying magnetic fields, that it is going to have a current that is actually going to go in that same direction. Because imagine that if I was able to transfer, I've got a current in a wire, and if I'm somehow able to transfer that current in a wire to the Earth, right, then as far as you're concerned, there ain't nothing happened, right? You know, just like, okay, went from the wire, went into the Earth. So now I'm going to get a current from the wire that goes like that. And now we know what's going to happen, right? Now we're back to the dipole, right? So we put a current at the surface of the Earth, and what's going to happen to it? It's going to diffuse away, it's going to lose amplitude. Okay. That's what happens here. So there's our moment that we turn off. We got this current, sometimes called image current. So, but that's a real current. There's real current that's going through there, and it is replacing. It's making sure that the magnetic field away from there is the same as what it was before. Okay, and now that current is going to diffuse outwards, downwards, and away. Okay, that's the wire. Okay, now, what about these guys? So I got all those currents that are going through there. Now I'm going to turn the generator on. What's going to happen there?
They can stay too.
Pardon me?
Well, if you've kept the other one, then they'll stay as well, because everything wants to stay in the same state. Isn't that what you just finished saying?
Yeah, but I turned the generator on, so I got no forcing function. So
Assuming there's nothing below the surface, right?
yeah, so there's just a homogeneous half space. I've got a generator that was hooked up. I now crank the generator on. So a couple of things happen. One is that, first of all, I'm going to get a current that's right on the ground just beneath the wire. And the next thing, I had all those currents there. Like I could have been measuring, the current density here. What's going to happen now?
Have the biggest change in your magnetic flux now. Have a spike and
Yeah, but instantaneously, all that change in the magnetic flux is going into making a current, an image current at the surface. So it's done its job, right? But imagine this, like there's a forcing function. It was the generator here that was working hard to continue to pump electrons into here, right? And now you turn that guy off. So that means I have currents, but there's nothing there to keep it going. So now you can think back to, remember that little dipole put in? I go, what happened? I turned it off. So now there's no generator. And then what happened? Okay. So that must be what has to happen to these guys. The moment that I turn them off, there were currents there, but now they're just going to decay away. So that's what happens to them. So the composite of these two guys is this. I've got a wire. That wire turns out to be really, really important. And then I've got steady state currents that were there that are going to, okay? That is a grounded wire in a half space. If we look at our currents for our half space, then this is what we had just before, and our currents as we go on with time after we turn things off will look first of all like this. So notice here, so here's, maybe that was a bit quick. So we're going to do numerical modeling of this. So we actually have got a region on the Earth's surface. There is a positive current here, a negative current here. So here's how the currents go. So that's how initially, that's the initial state. Now we're going to look at those currents. And at various times, they're going to look like this. So immediately after, or pretty soon after, you can see the concentration of currents right here. It's right underneath the wire. And then a little bit later, they're diffusing out, down, down, down. So the bulk of what you see there is just really the current shut off from the wire that is going down. Okay, so far so good. Here's our target. Okay, now, how's all this stuff going to play out when I've got a target that's sitting there, and I'm going to have a grounded wire over top, and I want to find this guy. Okay. So what we're going to do is we're going to try to, first of all, establish what that geometry is, and then we're going to switch everything on. And then we're going to watch how all the fields play out, and then we can see if we can see a conducting target or what the response is going to be. And then I'm going to be asking you anyway, where's the currents? And yeah, which kind of field should we measure? Because ultimately, you're going to want to go out into the field, and in an ideal circumstance where you kind of know what the geometry is, there'll be certain field components that are going to be particularly good, and there's others that are not going to be so sexy. So we're going to come back to that. So here's what's going to happen now if we put a block in a half space. So you can kind of see that there's a number of things now that are going on. First of all, here we have our block, so we've got a current that's coming in like here. So if this is a conductor, remember from this morning, there's going to be a negative charge on this side, a positive charge on this side. It's going to go up like that, right? That's our steady state. That's our DC resistivity. Okay, here's our current from the wire. And you can look to see how it is coupling with this guy, right? Because we've got wire here, here's our object, right? So my magnetic field is circular, so it is like smack dab through here. So I've got really, really good coupling. I've got excellent flux coming in through there. That looks good to go. So what's that going to do? Right, so now we kind of know about this guy, right? So the moment that I turn, so if my magnetic field is coming in this way, okay? So now I've got a flux that's coming in this way. I turn it off, and now there's going to be vortex currents inside here that are going to try to oppose that change. So they're going to be going around this way. So they're going to, and that's going to mean that we've got these conduction currents or galvanic currents that come through here, and then we've got these vortex currents. And so then the question is, how do all of these things play out? So I've got two types of currents. The inductive currents that are coming from this vortex, and also just these galvanic currents that are coming through there. So that each of them could play a role, and we need to look at them a little bit more carefully. So let's take a look at this. So first of all, here is an XZ plane. And if I showed you this and I said, well, here's the currents, I've got an A electrode here and a B electrode here, and you looked at this, you could even tell me, okay, is that a conductor or a resistor? It's a conductor, right? Yeah, so things are sucked in. Gotta help me out, right? This is a long day. Okay? Okay, so here's what happens. Here's what happens at really early time. Right, so here's the diffusion distance. So my electromagnetic fields from the wire, okay, are kind of sort of diffusing down, and I'm getting these vortex currents that are sitting. You see how circular they are? So those are circular currents there, and there's nothing. None of these currents are really flowing across the boundary. So there's no charges that are involved here. They're just circulating inside. And a little bit later, they look like that as everything kind of diffuses downwards. But you still this is almost perfectly. The main component here is just circular currents. Those are induced currents. Those are vortex currents that are just kind of going around. There is some overall currents that are coming like this, and those things are still kind of a galvanic, background current. And now here at a later time, these vortex currents are reducing in size, and actually there's a fair current, like a horizontal current that's still through there. It's not huge magnitude, but it's still there. And that's kind of a galvanic current. So he's causing some charges. And there's some stuff in here that's still a little bit circular, but most of this stuff is now basically going this way So it's stuff that's crossing the boundary, so there's charge buildup, and say those are basically galvanic currents. So you got currents that are going like this, those are the vortex currents, and then you got currents that are going through, those are galvanic currents. Galvanic currents cause charges, vortex currents are just currents. So that's what we have for our conductor. So early time, millisecond, primarily vortex. Late time, it's primarily galvanic. And you hear people who talk about EM, and they're always talking about, oh, well, that's those are vortex currents, or those are galvanic currents, or that. But that's where it's all kind of coming. Ah, all right, okay. Suppose we got that, and got a limited budget, and now you want to go out and maximize your return. So you've got a few instruments. The question is, which fields are you going to measure, and why? So imagine which fields. I mean, electric fields, EX, EY. So this is the X direction. That's the Y. Okay, so you got EX, EY. Can't measure EZ surface. And then there's 3 components of the magnetic field. Okay, so which should we choose and why? You're spending big bucks on this. Optimize. Pick a field. Pardon me? EX. Perfect. And why?
That's the way the galvanic currents were traveling.
Perfect. Perfect. So you get a gold star.
That's right.
We should do that. We should bring some gold stars. Okay, so we've got look what we've got here. We've got currents going through here, right? So we've got charges build up, electric field along here, the DC resistivity. You're good to go. But okay, yeah, good.
Symmetrical could be that way. Isn't that box same in any direction? If you would have it that way.
No, but in order to get charges on this side or that side, you need to have a current that goes
Yes, I'm
through
just
there.
saying you could measure EY.
Measure EY.
I mean, if you had the current along Y, what would be different?
No, but we don't have the current along X. So this is the only
Oh,
thing
sorry. I
that
just
we
got
got,
confused.
right? So if we measured EY right here, we'd have 0.
Oh, yeah. That's right. Oh, but you can also.
Well, I mean, eventually we would. We want to, excite the Earth from multiple polarizations. Okay. But the other thing here, okay, is you consider these the vortex currents, right? So how are they going? They're going like this. So that means that their electric field is also in the X direction. So excellent choice, right? Yes. Because you're sensitive to the charges, but you're also sensitive to those currents. Okay, good. EX, what about H field? Pardon me?
So why?
Good, HY, perfect. So measure the Y component here. Be good to go. Any other component for H?
Z.
Yeah, you're just like you're acing this stuff. You probably read the notes. Okay, so that's right. So if we think about a wire, right, and the magnetic field from a wire, right, so it would have a Y component, and it would also have a Z component, as long as you know a wire. So here's EX, and look what happens with a conductor. So there's the half space. This is early time 10 to the minus or 0.04. And then look at this, 1 millisecond. Look at the character compared to the half space, and 10 milliseconds. So EX, perfect. EY, also really good. Right, so we've got this little bit of distortion here, much bigger at 1 millisecond, and at 10 milliseconds, it's good. DY is good. And Z, so right over here, right over the middle, you don't really see anything, but you do have that advantage of the currents kind of coming, up on one side, down on the other. So, and if you look at the difference between the half space and the conductor, you see, there's some pretty significant signal. Good. So EX, in this particular case, EX, EY. But the point is not like, okay, which field should I go measure, right? I mean, you're not going to go out of this room and say, wow, I've got a ground environment, I'm going to measure EX, right? That's not such a bad idea, but the point is just to try to kind of work over. Okay, so what's going to happen in this next case, where we have a resistor. So now we're going to do the same thing, put a resistor in, and you can tell it's a resistor, right? Because you can see how it's kind of going around the body. Okay. What are we up against? What's going to happen?
The galvanic currents will get blocked. The vortex currents just won't be very significant because it'll be a lack of vortex currents in a very small box compared to the same currents trying to go through the rest of the half space.
Good. Anybody else?
Current charges will be reversed.
The charges will be reversed? Okay. Anybody else?
It's a resistor, right? It has an internal current.
Yeah. Oh, that's cool.
I know.
I gotta have to buy you a beer after. I'll share. I'll tell you what. I'll share half of the wine that they served at lunch.
It's very generous.
Okay, so yeah, we'll get progressively more punchy as the day goes on. Yeah, so let's see what happens. So initially, okay, we got currents that are coming through like this, right? Turn the wire off, so there's going to be some induction. So we can see, it's kind of, there's currents coming in through here. A little bit later, stuff is diffusing down. Later, stuff like that. So, I'm sorry, I forgot your name. I should have. David, yeah. So David was right. Basically said, like, okay, we're going to have continual galvanic currents as they kind of diffuse through. Those galvanic currents are going to kind of go around the body. And inside here, there's no vortex currents that are being generated. Remember, there's a change in electric. There is an electric field, but there's no currents because there's no conductivity. So when we got a resistor, then we start off with galvanic currents. And at mid-late times, it's just, we still have just currents that are kind of going that way through. There's nothing that's built up that's got vortex. So everything is kind of going through. Everything is just, so since there are currents like that, that means that the big guy on the block are just going to be these charges. And for that, which fields are we going to measure? EX, right. That's going to be, are we going to see much for magnetic field?
No. You still have vertex current.
Pardon me? Yeah. So there are, so here's the EX field. So we can see for a resistor, we still see a significant difference here between this and the half space. BY, yeah, there's a little bit. I mean, there are currents, but they're weak currents, and they're gradually fading away. There's a tidbit. And BZ, yeah, just hardly much at all. So that's the ground source, which people tend to think, well, that's really simple. And then put a little block in. First thing you know, there's a lot of stuff happening. Our data summary is as follows then. So if we've got, here's our half space circuit over here. We've got a conductor compared to half space with a resistor. See really good signal in EX. BY is good for conductor. BZ is good for conductor. But really it's EX. This, for anybody who's connected with the boom in electromagnetics for hydrocarbons, and we're, the seafloor EM probably injected more money into electromagnetics than 100 times more money into electromagnetics than has been input in all the other years of looking at stuff. You can see why they chose the experiment that they did, which is basically, okay, I got a boat. I'm going to, first of all, I'm looking for a hydrocarbon reservoir at great depth. Okay. So I'm going to be, and it's a resistor. So that means conduction effects aren't going to be particularly important. First class is something that's galvanic. So I'm going to tow an electric dipole, and I'm going to measure the electric fields away. And because my hydrocarbon layer is 3 kilometers beneath the ocean bottom, I'm going to have a streamer cable that's 9 kilometers long in order to see that. And that's exactly. So far so good. The thing we haven't talked about is coupling. So remember, even in DC resistivity, it was like, okay, it's getting complicated. And here, I think there's a few things that you can kind of intuitively grasp. Like this guy is going to be good, right? If I've got a current going like this, right now I'm going to have good DC resistivity. We saw that before, and I've got a really good EM coupling because I've got something coming in on the face. This guy here, probably poor coupling, certainly from the point of view of EM. So basic principles kind of have, but when it actually comes down to details and trying to figure out, okay, exactly how those fields are, which one's going to be bigger, it's too complicated. I mean, it's basically for me. So that's where, yeah, for most of these, you just immediately go to some kind of numerical simulation, see what you got. So let's do a case history, simple case history, the deck and traps, and I'll take you through this guy. We presented the disk in India, which I must admit was quite an experience because we had decided that India is like a really big place, lots of people, and they have a lot of computational people, a lot of geophysicists. And so we thought, well, in order to be effective in India, which is what we're trying to do, we should probably go in maybe 3 different places, like Hyderabad, Mumbai, Bangalore, and Delhi. Just really go around because India is such a big country. So that's what the initial plan was, and then we talked to was NGRI, which is their National Geophysical Research Institute, headquartered in Hyderabad, and they got really excited about what we wanted to do, and they said, look, you just come to Hyderabad, and we'll arrange everything for you. We'll make sure that people from all over India come, and we'll actually extend this so that we'll have another 2-day EM workshop after this. So it turned out to be a 4-day affair, and yeah, really people just actually came from all over, and it was a great event. I was talking to one student, he was actually from the northern part. I said, how did you get here? He said, well, I took a train. I said, well, how long did it take you? He said, well, yeah, it was 33 hours. And I'm thinking, there is no way in North America I could get anybody to go more than 32 minutes. Never mind 32 hours. But at this meeting, there was a guy named Kurt Strack, who is kind of a founder of something called LOTEM. And it's a long offset time domain survey. And a number of years ago, they did some, I think, kind of pioneering work on the Indian flood basalts. So here they were here. So here's the setup. We've got a region in India, it's this part here. And yeah, how many people know what the Deccan Traps are and why they're important? Pardon me?
I know what they are, but not why they're important in your.
Anybody? Somebody tell us what the Deccan Traps are. Yeah, yeah.
Well, the only reason I know about them is because you can't shoot seismic.
That's exactly the point. That's why this case history is here. Yeah, okay. Deccan Traps. Anybody? How many people have heard of the Deccan Traps? Oh, hey, not just about half. Okay, and pardon me?
Just heard of it. Nothing more.
Do you know when they happened? Do you know what they were? What?
They mark a boundary in time of like a significant event. Knock out a species.
Yeah, we'll get to that in a sec. That's good. Okay, so these are huge basaltic flows. I mean, immense, that lasted for a long time. And I don't know, millions of cubic kilometers of basalt flooded out, along with a lot of gas from the Earth's interior. And at one point, there was a lot of discussion that people felt that it was the Deccan Traps that really got rid of the dinosaurs. So there's always been these two competing things, that it was either the dinosaurs or the Deccan Traps. And the Deccan Traps, when you talk about it, so there's that layer of, so from the iridium, yeah, you go around the world, there's this great big, an extensive layer of iridium that coincides with the dying of the dinosaurs. And so that was actually felt like, okay, it's really the meteorite impact that caused the demise of the dinosaurs. But for many years, because both of these things happened kind of about the same time, they weren't really sure who was more responsible, or maybe that there was some kind of cause. It might have also been that some of the Deccan Trap gases actually put enough stuff in the atmosphere, a little bit of global warming or change, and then, or cooling, I guess at that time, maybe that kind of compromised the immune system. So, of the dinosaurs. So the point is, these Deccan Traps geologically are important. That's what the development of the Earth. And then for people, Indians who were interested in hydrocarbons, these things were an absolute nightmare. There's basalt. Basalt's really tough to do. It could shatter, all kinds of internal reflections. And the question was, what's the thickness? First of all, is there sediments beneath here? And if so, what's the thickness of these guys? So that was the question. And at the time that we were doing that, we felt that sediments were, that there were sediments, but they actually increased in thickness as you went along. Okay. So the goal was to try to determine how thick they are. They did a big DC resistivity line across here, came up with an interpretation. So this was actually their interpretation of sediments, and that was saltic regions. But I don't think people felt too comfortable with that profile or assessment. So they wanted to go and do something electromagnetic. So that brought in the LOTEM system. So it's a long offset time domain EM. So you've got a transmitter over here, and maybe, this is like 10 kilometers away. So this is grounded wire, and you're a fairly long ways away, and then you can measure both the E fields and the H fields. So if you're going to do a survey, you need to do a sensitivity test. This is kind of crude, but this was done a long time ago. So the idea was that you had the traps, which may be about 150 ohm meters. They could be anywhere from 1.5 to 3 kilometers. Then you have sediments underneath, and then basement. So just done on 1D modeling. And what was done here is if you look at the analytic formula, you look at the asymptotic expansions, there's sort of an early time and a late time, and you can convert each of those to apparent resistivities. So at the early time data, you ended up with something that looked like this. And these three curves correspond to whether the upper level of traps are 1.5, 2, or 3 kilometers thick. So you could definitely distinguish that there's some sensitivity to the thickness of the traps. And these are the late temperatures traps. The other thing is, if you're given a particular background, and at 3 kilometers depth, you've got sediments that are 20, 50, or 100, again, you can see that they're affecting the data. So remember we were talking about sensitivity analysis? That's kind of what this is. You change your model parameter, see what the data are, and then the question is, okay, is there, is this big enough that it's above the noise level and you can distinguish it? Yeah. So the processing of the data was pretty minimal. You could do 1D inversions. Actually, these were just simple layered parametric inversions. But the kind of interesting thing was that, so this is line L here, so we're going across here. So what we're seeing is an upper region of 80 to 140 ohm meters. So that's the salt traps. And then underneath there's this lower resistivity, 16 ohm meters, and then underneath here's 3000. And you can see that the thickness here is pretty substantial. It's about 1 kilometer. And if you go to R, and then subsequently, well, let's go to G. So this guy down here, see, you got kind of that same structure, but this is thinned a bit. And then if you go to K, it's gone. So this was really interesting. This is completely counter to what they were anticipating. They thought, oh, there's sediments that should be increasing towards the side for whatever reason. And this, this showed something that was entirely different. Sediments are biggest up here, less down there. And what's important, as I mentioned before, is the conductivity thickness product here. So that's what was generated for here. So take this value, this value, this value, and then you plot these things on a map. And now what you have here is it's a conductance map. So this particular point in here, it's got the highest conductance, so biggest product of thickness and conductivity. So they actually drilled here on the basis of that, and got like a pretty reasonable result. What they obtained from the inversion was that there should be a layer of basalt and sediments, and then basalts. And actually, the boundaries here kind of come pretty close to what they did. So what was here, this was a drill hole, and then here's the formation, and you've got sediments up to about here, and then you've got, traps up here, you've got salt, and then you've got sediments down to about here, and then so crude interpretation, crude data by today's standards, but kind of served a purpose and was overall successful as well. Okay, so that's, I show you that I think it's just kind of interesting. Plus, it's like a bigger kind of thing. You've got transmitters that are 3 kilometers long, and you're like 10 or 15 kilometers away from your receivers, and it's just a different geometry. And you're looking at bigger things, sort of something more in that tectonic. But it's again all of the same basic physics. This is something I think that might resonate with the audience, so I'm going to put it in. It's a synthetic, but it's basically kind of looking at both DC resistivity and EM. And you're at the perfect point for doing this now, right? Because remember DC resistivity, we put this thing in, and then we turned it off, but we were mostly interested in what was happening here, that voltage. We converted that to apparent resistivity, and but now we understand, like, okay, I'm going to turn it off. Well, wait a minute, I'm turning current off. That means there's going to be a lot of electromagnetic induction. That means there's going to be stuff happening. And that's exactly what does happen. If you're sitting out here, there's going to be a transient that you're going to see. It's effectively what we've been talking about all afternoon. And it's going to come back like that. What you're generally looking for in most of these is the IP signal, which is going to occur perhaps at a later time, but maybe be involved in that. That we will talk about tomorrow for people who can stay. For today, we're just going to kind of look at this guy. Because these data here are often A, not collected because you're not sampling early enough in time with a DC experiment, or B, they're just thrown away. So what I'm going to do is to show you that those data should not be thrown away, and they contain very valuable information that could actually complement the DC part of your system. So here's where I've got a system like this. In this case, we're going to use a horseshoe loop. So it's going to be more like a gradient array with currents going like this. Turn it off, and we're going to see this EM portion, which is traditional noise. What we're going to do is to look at 4 blocks here. So here's our current. And A1 is going to be a very conductive block. A2 kind of moderate. That's resistive. And this is the same as the background. Here's some cross section. So we're going to see if we can't see these guys both with a DC resistivity survey, and then also how we would do with an EM survey. Same setup. All we're doing is measuring earlier data. So if we look at the DC resistivity data, so that's taking this point here, right, just before shutoff. And then plot the voltages up. Well, we already know from this morning that the voltage is going to be really high at the current ends. So it looks like that. But if you convert that to apparent conductivity in this case, and that means taking all those geometric factors in, you can see that, oh, we've got 2 conductors and actually a resistor. So there's a lot of information here. And this guy's bigger than this guy, so first pass through, you got some information just for the data. If you look at the time domain data, now remember we've got this wire. So we got this wire, part of it's this way, right? And then we've got 2 other components. So everything's lighting up the earth, right? Each little segment of wire has got its own inductive effect. You've got currents that are going all over the place. If you look at early time, and basically what you're seeing is just the effect of the long offset wire to the back. And a little bit later, looks like that, later. So just to make sure you've got this. So this is a plan view. Okay, so the wire is like this. Okay, so we turn this off, right, and we're measuring an X component. So we're measuring an X component, so it's basically this guy here that we're seeing. And that is going to diffuse down. A little bit later, it's kind of diffused like that. But it's getting blocked kind of by this high conductor here. And then gradually, things change, and you end up with these as final voltages. And if we look at the decay curves, so let's look at A1, A2, A3. So here is the blue is the half space value, and then this is the block with the half space. So there's actually really significant differences there. here's A2, and here's A3. So again, we don't see very much difference in the inductive level from a resistive block. Okay, so that's okay. But these two conductors we got. So now we do a DC resistivity inversion. So we're going to do a 3D DC resistivity inversion, a gradient array. The thing with a gradient array is it's only like a single source. To some extent, it's kind of like inverting gravity or magnetics. It's just like you've got a plane. You just have a single source. You really don't have any depth resolution with the gradient array. However, we can do the same thing that we do with magnetics. Remember, we've got this 1 over r, 1 over z cubed, depth weighting put in. So we'll take the DC resistivity data, gradient array, put a 1 over z cubed weighting, and invert it, and we get this up. So it's not bad, right? We got, conductor here, one there, resistor there, cross sections. Not bad. Okay. What would happen if instead of using those data, however, we use the EM induction data? Well, if we do a full 3D time domain inversion of this, this is what we get out. The thing that's really great about this, I mean, first of all, these conductivities are somewhat better than was obtained with the DC resistivity. Secondly, there is no depth weighting on here. So now because you've got waves that are progressively diffusing in, it's like you're taking snapshots with different kind of sensitivity. So there's depth weighting that's coming into it. And thirdly, this is done with data that usually are usually dismissed or not bothered to be acquired. So how good is that, right? So you don't do anything else. You have the same equipment, exactly the same thing. The only thing is you need to have, be recording at a higher sampling rate, catch the early times, take those times, and then get this up. So ultimately, you use both the DC data and the time domain data, and you've got something extra about what's going on. So this kind of summarizes that those are the true conductivities. That's what you get with DC, with depth weighting. That's what you get with EM. That's it. Ha. Any questions?
I guess when you're looking at that, you still, when you shut that pulse off, you're still going to have background IP effects there, aren't you, superimposed on your EM response?
Right.
But your stream potentials and all those other things make up your IP response. How do you actually separate those out from one another?
Right. So that is very much a topical discussion. I've got quite a bit to say on that, but I think I'll leave that to tomorrow. Because there's a few things, and both with galvanic and inductive sources, that it'll turn out. I mean, I'll give you the short story. At very early times, we think we can use the inductive responses and get a conductivity that's not too contaminated with chargeability. Okay. At late times, we've just got this chargeability data that's probably uncontaminated by conductivity. But there's this intermediate time that's a blend. And the trick is to, okay, what can you possibly do to separate these things out? There's quite a few ways of approaching it. The way we're approaching it is to invert the early time data, get the first, or the DC data in conjunction with that, use that to get a conductivity model, do a full 3D Maxwell forward modeling. That gives you the fundamental response that are hopefully not contaminated with chargeability. And then subtract that from the observed data. So now you're left with an observation minus the fundamental, which hopefully is just, well, by definition, is your IP response if you've done that correctly. And then you invert the IP data with the same linear thing. So we can take you through that, And there's two parts of that that are extremely interesting. First of all, it's interesting enough for the galvanic sources, where you actually have a DC asymptote for it. The part that's much more challenging is when you have an inductive source, because now the IP response is going to be developed, differently at different times. Actually, there is one thing. Maybe if I have 2 minutes, let me just do this. We have a tutorial on EM, controlled source. And what might be of interest here is this. So what we're looking at here, this is depth and resistivity. So here's an ocean, and then we got a sedimentary layer underneath, and then we might have a hydrocarbon layer. So this is maybe a kilometer or two kilometers, and our goal is to try to find this guy and design an experiment that's useful. So just the same as we were talking about all day, we've got a resistor. Okay, so we probably want to have a galvanic technique, and the easiest one to use if you're on board ship is to pull a grounded transmitter. So you put a electric dipole here, and now you measure the electric fields away from you. So it's just a DC resistivity experiment, except you're kind of doing it inside. And the other thing I was mentioning is that if this is a couple of kilometers depth, then that distance between your transmitters and your end receivers needs to be 6 or 8 kilometers long. So these are huge, huge operations. I mean, you look at these guys streaming cables out for 10 kilometers. It's, it kind of boggles the mind. Anyway, it works for sulfides too, just a sec. The thing that is so interesting about this and caused so much consternation, and in fact for just about everybody that I know, really caused us to kind of sit down and try to think about things, was something called the airwave. So here we are, you're sitting in the ocean, and you're putting energy out. So we have this electric dipole, and so there's going to be energy going through the water, energy going through the sediments, and if you've got a hydrocarbon layer, there might be energy that comes through here. But there is actually energy that goes up through the ocean, and there's this Earth-air interface, and we can get an energy path along here. And this was the airwave. The seismologists, here it is here. So as if there wasn't any hydrocarbon layer, we just have this background model, and then you're kind of okay until you hit about this region here, about 6 kilometers away, and then suddenly you see how the shape of the curve changes. And the shape of that curve is changing because now you're getting energy from a different, from a different path. And this guy is swamping the signal that you have from the ground. So the hydrocarbon layer could potentially be buried in that, but if this is a noise, it could be masking the thing that you want. Yeah. So everybody was involved in trying to understand the airwave and how to remove it. And if you know seismologists, we all know seismologists, they're really interested in up and down going plane waves, and they can do deconvolution and subtract things out. And so they were trying to cast the electromagnetic problem into seismic. Because okay, I've got a hammer, you look like a nail, right? So if I can get your problem into something that I understand, I might be able to do something. So that's how they were approaching it. The EM geophysicists were scratching their heads saying, like, I just don't get this stuff, right? Or can't really quite connect. And then people were really trying to decide, like, okay, is this really an airwave, or what's going on? So a huge amount of effort went into just understanding. Peter Vidal, a really famous electromagnetic geophysicist, wrote a paper one time in the early 2000s that mathematically showed unequivocally what was going on, and by doing the appropriate asymptotic expansions, showed that, yeah, this thing should be dominant at that point. Wading through that paper is not a trivial thing, but he kind of showed that. What I'm going to show you now is a movie. It's going to take 20 seconds of your life, and you're going to see that movie, and you're going to wonder, what's the thoughts? Why is everybody so confused? Because it's one of these things, and again, this is the advantage of photography. You look at it, you see it, and it's like, oh, how simple was that? Of course. So what we're going to do is look at this guy here. Okay, so let me set the scene. What you're going to see, this is a time domain representation of the fields. There's an initial underlying software that credit is given to Whitemuller, but the development of this movie and a lot of the work that went in belongs to Sagi Kent, who's another one of my co-presenters. He was with me in East Asia and South Asia. And what we're going to look at here is now a horizontal electric dipole that is switched off. And we're going to look to see how the energy propagates. So here's the ocean, here's the sediments, here's the hydrocarbon layer, and more sediments, and then here's the air. And what I want you to watch is the wavefront, so you can see where things are at any particular time. And you'll remember the diffusion distance, right? Okay. So if it's more resistive, then things diffuse faster, or if you want to think about it, they travel faster. Okay. So when we're sitting right up in here, it's sort of, they kind of look about the same. But we're gonna set this movie going, and you can watch a couple of things. First of all, the difference between what happens here and here. So this is ocean, so it's more conductive, so it's going to go more slowly. This guy here is resistive, so he's actually going to act like a bit of a wave guide. You see what happens. And the air is also effectively going to be a wave guide, so we can see what happens. Okay. Excitement's high. Oops. Go. Okay. Okay, so actually look even here, right? So we started from here. Look how far this has gone down. This. Right, so that's what we'd expect, right? Just on the basis of diffusion distances. And now you're actually also at a critical point too. Watch what's that? So this energy is just hitting this interface.
What are the vectors?
Pardon me?
What are the vectors?
Vectors are the electric field directions. So some of them are pretty small. Okay, so we're just getting into that. Okay, how cool is that? So you can see what happened here. We got down here, and look, he's just zipping along there, right? So this guy's going to zip along here, and then he's also going to radiate back up here. And here's our receivers that are going to be along here. So the first thing that we really notice is that there's a lot of energy that's coming along that path. So here's another critical moment. So he's way up here, zipping along. And now this wave here is just hitting the air. Air, resistivity, completely infinite. Okay. So things are going to blast along essentially at the speed of light. You see that? Okay, so now it's kind of all the way across. It's kind of across there. There. Okay. So actually, I'll show you one more. This is there's something called a pointing vector. Anybody know what that is?
Propagation of energy, basically. That's the vector that shows.
You're trying to take some of her gold stars.
I know.
Okay, so the pointing vector is E cross B, and it tells you the direction in which the energy is propagating. So it's kind of interesting. So now we're just going to look at the same thing and just kind of look at where the energy is. And I want you to look, I mean, one of the main things is along here, because you'll see that this electric field that's coming in here is actually going to get torqued basically straight down. So the electric field is going to go down there, and that's going down because of all these charges that are built up on the interface. So we come back to the charges, right? And then the B field is perpendicular to that, and it's just going to propagate along that. So you can see how the energy is propagating. Oh, shoot, what happened there? Look at that. Look at that, right? So it's coming along here, and then the energy is propagating along here, and then it's actually going to be radiating out from both directions. And it comes down. Okay, so this, I don't know, I show you this for a whole bunch of reasons. First of all, it's really interesting, okay? Secondly, it caused such a consternation, as I said, in industry and people are just not really sure what's happening. And then Peter Vidal comes along, he shows mathematically, like, okay, this is it. And then somebody else comes along and he actually makes a time domain modeling. And modeling in the time is important, right? If you model this in frequency, yeah, you can get things that it's really hard to really completely untangle things. You model in a time, it's just like obvious. It's so simple, of course, that's what's happening. So things like that, I think, really add a lot of understanding to what's going on. They show you the power of visualization and numerical processing to kind of integrate with what's going on. Okay, that's plenty. So we're going to have a short break for coffee. We can do 50 minutes for coffee. We'll come back. I'm going to pick up natural sources. So we're going to do the MT. Then we'll do the IP and then a wrap up. And I think we can go get up. Oh, so this red line is what happens in the test signal you get if you have the right? So no problem. You definitely
at the end, if we have still going.
No, it's already not.
When I drop off my little kid.
We're not. We're done with our
Can you need to have anything installed on our laptops for the first one talk or no?
Yes. No, let's see if I can get
Obviously.
I tried to install the single tape, right? Last night on my Windows and it didn't work. Windows we're trying to fix. Windows is tricky with Python, isn't it? Well, yeah, it's the laptop that company gave me and I hate Windows, but it's tricky. That's when you go to open source, always a problem. Yeah. You know, like, get us, Really? So we haven't gotten it up yet, but it's on the radar. But you can use it as your notebooks. Okay. And I'll run it live on the web. And so and that's a Unix machine, so it's so much easier to just install it if you want. I guess if I have a virtual machine, it might be closer. Yes. Yes. I did in my PhD. Excellent. Yeah, we have that right in Sweden. Oh, right, yeah. Lots of things. Yeah, so I'll just. So what's my guest? Sure. Yeah, it's great. Okay. I'll keep the super stuff pretty short this time. Yeah, I think that's. Sounds alright. And some of the numbers.
Yeah, exactly.
Yes, just the red bus. Just an instrument. It's a red bus. And of course, you get on it just in some train station, and not teaching you what to do. So they can do that.
Well, let's maybe try and get a count or just like a rough hand raise to get an idea. Budget. That'll be good. That'll be great.
Yeah, I think. Okay. That'll be good. I think that's probably all.
You used my first email that the other meetings going on tonight. The Norwegian like Andy Huckhuber is talking geophysics for geotechnical applications.
Oh, when is that?
6 o'clock start, 5:45 is ready.
Oh.
Still Andy Huckhuber.
How do you spell it?
Huber.
Where's he from?
He's not Norway. Anyway, he's currently posted in.
And then he's coming here and he's giving a talk for ACG.
No, not people. Also, mechanical engineers.
You know? Oh, right, that's right, yeah. I don't know when that starts. Yeah, no, I think.
I think you have to go there.
Yeah. Yeah, otherwise. You're just saying? Yeah. Because we're trying, that's another group that we're trying to change. Well, you can be our spy.
I will be there. I remember that. Yeah, well, I mean, it's, communication varies, but hack away at it. Just find the right applications and case histories.
They like lots of cross plots and whatever the plot is like, it's straight line on X plus B is the theoretical does V squared term in it.
Oh, yeah. Well, if you work on a reduced enough range, let's go get a bit of coffee and see what they did for lunch.
M price cleared as well. M price done speed cleared.
So after this, just pop this down here. By the way, go upstairs, see how the water's done, and then you come and clear this, clear upstairs. And then we'll talk about anything else that's left over.
Yeah, I think something.然后本来是20号，我认为我是然后做内容的剪的，然后大概半个小时左右，然后建了他的观念。这边还沟通，还有看，这次我们去看海豚，那个
然后还有一个就是就非常那个最早的这个复活特别基本上见过但是你没有问题。他们的但是你去这个好像我没有考拉不高，但是到他们的种。这样我只做是给你上看出来他们说的不是照相还有导演，这一次去的就挺快。好软的包。吵架出来打架，生意啊，太吓人，然后过来。一个大的社群，然后基本上大的。累不累？不累啊。有感觉眼睛又干又涩。就是。对呀，我也好久，你应该更久了，你应该好多年了。
讲到海洋电磁那个，海洋电磁对，海洋电磁不是有四个功吗？它那个它那个管上那个，它不是那个黑线不是有个管的地方吗？然后他说的是，我没大清楚，但是没跟上，没大清楚它是哪个波儿，是因为哪个波的影响吗？是不是空气吗？我以为海洋电磁空气流应该是传导的，后来他今天一演示好像不是。它是传到海面上的时间稍微久一些，然后在海面上。我那会儿是做了海洋电磁。
还有2块，一个就是它的
他在那个 Radar 里面，也是导播创作的，美国导播。
对，在那边
对。因为他那个电阻率太高了，
反差太大了。
它在空气中其实光速传导的。对，我也不知道它那红线什么东西啊，红线啊，对什么什么。而且它这个海洋电磁的源头是水平电路机不是它那个源是，因为你要是 HEG 的话，就相当于一个小线儿，那你肯定要通电嘛，人家2个电网是有线不出口的，它这个是。怎么这个线接了呢？就是如果你要是有一个电缆这样接过来的话，就相当于一个回路了。因为你这个点基本上就是离海面大概5米的位置，然后你要是不可能放一根就是单单一根线在那儿。
单单的一个线，你看见你这个
我们现在
它就是一个像一个安全那个，它是那个电是小的，是就是2个都是哦，你出去一个就是第三的一个 source， 然后就像那个antenna一样，但是一个是那个是。
哦，那你就是直接把它传到。
对，传到水海里面。
哦，我知道那个接收机是用那个什么，就是有那个开关，它直接把那个抽起来的。那个发射源是怎么？
在里面，发射源。
然后，那它怎么收？
自动收的时候有一个高感控制。然后，
我知道他那个接收的时候是开始控制产品放一个重物啊，
它下面有个重物，然后你升起来之后，对，把那个东西就扔到水里。
So how you going? Enjoying it?
We're on notes tonight just to make sure
Get grasp.
Yeah.
反正我知道每一次去前进
That's right. Yeah. Yeah.
看它 M 的 source 如果是用的 control source， 前面它也用了一个 pass， 就像 MTT 也它是那个就没有事，分辨率相对来说，也不一定看你的其实。对啊。
本来这个电子对于咱们天然来说，
the IP effects
好像海洋之间才能
to discuss, because I guess we had this conversation about Russell Waterman mentioned IP effects and how they manifest in
你也没工作。
my interest asking about those.
He's going to talk about this for a second.
相对来说，
Yeah, I'll try. Yeah, just say I'd like to get in there and see how it goes.
Camilla is good. Minus 3.
Oh, really?
My son lives in Cambridge. Well, I hope so. I think he was in Australia for 40 years.
Yeah, that's interesting.
I haven't seen him for years because he's very sick. His office next door.
He was part-time before that.
I've seen him last yesterday.
Step into your seats. We have to take a picture.
Oh, we don't have to take a picture, but we're just
Going.
Do we need a photo?
Yeah, we need a photo. Who's got the photographic eye? I guess we could put the light on up here.
You can go start. You can run. Where you going to start?
Okay. Well, I was trying to turn the light on, but I couldn't. Let's go in the back here where the lights are. And we should get somebody to take it.
Studying at your session.
It's mandatory. Yes. I had another coffee.
I'm ready. Bring it on.
Bring it on.
Oh, you guys need to join the photo? Okay, sorry. We just came to answer questions. You don't take out.
Yes, let me see your here. We want more like, we want I can't see people that suddenly. We keep going.
We have to go.
Okay, let's go. Let's go. Okay. Yeah. Come on. No. Oh, yeah. Perfect. Okay.
Yeah.
So what we're going to do now is have Lindsay give you enough background about SimPeg and some apps, and just at least enough to kind of get you going in case you want to spend some time tonight. Okay? And then after that, we'll pick it up and we'll do the natural sources, the IP, and the future. Thank you.
All right, so I'd just like to show you where we can actually access a lot of the resources that have been developed, both for the course and then some of the things that the course is actually built on, like SimPeg. So the site that you can start at is GeoSci.xyz. We've got a number of resources here. So the GPG is actually what we've used for an undergraduate geophysics course at UBC. So it's got a nice overview of basically all of the geophysical methods at sort of a once-over lightly level. It was aimed at mostly geologists and geologic engineers, so it gives a pretty good overview. EM is the one that has been developed for this course. So this is where you'll find all of the case histories that were up there today, and also where the apps are. So we'll come back to this one. And then there's SimPeg. And so SimPeg is the open source software package that we've been working on at UBC. It's all written in Python, and it's completely open source. So you're free to use it, contribute to it, get in touch with us. So there's a number of resources here on like how to actually connect with people if you really do want to get up and running with it. Because there is documentation, but of course, once you want to really start doing some different things, you'll want to get in touch. So to run the apps that we've seen today, if you start from EM GeoSci, there is an apps tab here. And so we actually have two styles of apps. The EM apps are the ones that Doug has shown you so far today. And these are really meant to be things that you can jump in and start playing with right away. And so the code is hidden. It's basically like GUI style apps where you can run the code with slide bars and entry boxes and things like that. The other one that we have, and there's just a handful of notebooks in here right now, we're hoping to continue to grow this, is the simulation notebooks. And so in this case, we have exposed all of the code. So if you want to see how to run a frequency domain simulation using SimPeg, that is there. And so you can reproduce actually a number of the examples that we're showing today with some of the notebooks that are here. So I'll show you just how to actually access the apps and get up and running with those. If you want, you can actually download them and set them all up. If you're familiar with Python and GitHub, there's instructions on how to do that here. That'll run it on your local machine. What I would recommend for most people is try it out on Azure notebooks. So this is run by Microsoft. So if you follow this link here, you'll get to a page like this that is going to show you right now just the contents of the library. So we've got a whole bunch of apps here. And so say you want to be looking at the DC cylinder 2D. That's the one that we looked at this morning. So we can click on that tab. And so right now, because we're not signed in, it's just going to take you to a static view of the notebook. So you can scroll down and see it, but that's not all that interesting, right? So what you actually want to do is then clone it. Sorry, this is a bit big. So you'll see this button that says clone. So if we hit that, what that's going to do is actually then make a copy of these notebooks to your account. So you have to have a Microsoft Azure account. If you didn't have one before, you can create it. It's free of charge. And then so it'll land you on a page that looks like this. It says, do you want to make a copy? We'll say yes. And so that is now just making a copy of all of those notebooks tied to your account. And so if you want to actually go in and make notes in the notebooks or change some of the parameters or things like that, it'll save. So it is now your personal copy of the notebook. So we can open this guy up. And so what's happening right now is Microsoft is actually spinning up a server somewhere and giving us some compute space to run this notebook. And so there's the easiest way to go in and run it is you see at the top where it says cell. Can you guys see that from the back? Is that okay? So we go cell and then run all. And so all that's going to do is run and execute each chunk of code. So it's going to go through, and if we scroll and look at the top, what's happening right now is it's just installing the packages that we wrote to actually build the apps. So if you wanted to load this on your own machine, you can install this. So that's just downloading right now. And then once we get that, it's going to go ahead and import the packages. And then it'll run the app. And so one thing to help just sort of when you're using this, circle is full. It means it's computing something, it's thinking. And there'll be a star in that cell when it's thinking about that cell. And unless it changes to a number, it's done. And so now you have the app, and you can go ahead and play with it. Are there any questions or other things that you'd like me to point out with respect to GeoSci or the apps? It's very quick once over, but there's also, if you didn't catch all of that, on the page here, on the apps page, there are actually some instructions on how to run that and get that all going. Another thing that you might want to check out from this site is also the case histories. So this is where we've got a number of write-ups on the case histories, some of which were presented today. So you can go ahead and look at Mount Isa, for example. And then there's a couple ways that I want to show you of how you can actually contribute to content here and get engaged in some of the conversations. So if you see a typo or something that you think should be fixed or added, you can actually edit the page. And so it won't go live right away. It's not the same as Wikipedia. But what'll happen is we'll get a notification that says somebody fixed this. Do you want to make that live? And then we'll get in touch and we can get that live right away. And then the other thing that you can do is add comments, questions, and things like that on this page. And we'll again be notified and can jump back in. So there you have it. Anything else you want to point out, Doug?
No, I think that's great. I think that you've just condensed about 25 man-years of work into 3 minutes. Maybe it's 35 years of man, I'll tell you. The group at UBC has been absolutely incredible. The amount of work, effort, thought that has gone into developing these open resources, I can't even try to convey. It's been a consuming effort for a couple of years now, but I think what has been developed is something that can really make a difference in the long term. Going to open source. When you come tomorrow, Lindsay will give you a breakdown about SIMPEG, all the open source modeling for doing forward simulations and ultimately inversions. There's a lot of inversion stuff there that's already. I think it's going to take everything to a new level and allow people to really understand what's going on as well as to interact. So for us, it's a big paradigm shift for what we've been doing. But as I said before, everything is kind of coming together, and yeah, it's just this incredible group of people we have at UBC that have made all of this happen. So you come tomorrow, talk more about SIMPEG, more about open source resources, got tutorials on inversion, programming, all kinds of stuff. Okay, so now we're going to switch gears. How you guys doing? Good. Okay. Natural sources. I was surprised. There's all these people who were talking about magnetotellurics, right? Like, okay. Great. Whoa. What happened? Okay, EM, natural sources. Why do we care about natural sources? What's the big deal with MT? All the MT people? Why?
Someone else?
Can I get all the gold?
She's tired, like her bag so weighted down with gold stars. Why MT? Pardon me? It's free. That's one thing. Right?
Yeah, there you go.
You don't have to be, yeah? You don't have to take gap geophysics for your transmitters.
Great magnetician guys. That's how we get the HX.
Perfect. Okay, all of the above. Good. Okay, so I'm just going to talk a bit about natural source techniques.
Yeah, you
MT, and
I
J60.
about MT, so.
Okay, what's our motivation? There was somebody I was talking to who was interested in volcanoes.
That was me.
That was you.
Yeah.
Okay, so
I was.
That was in your previous life. Now you're in mineral exploration. Good job. Okay, so we got volcanoes, base of the salt, geothermal energy, large groundwater, big mineral deposits, big porphyry systems, tectonic plates. The thing about this is scale, horizontal and vertical. And we talk so much about seeing deep, right? So for the controlled source transmitter, the big thing is your magnetic moments, your product of your current times your area. And the thing with that, though, is that if if you've got a control source, then basically you've got this geometric decay of 1 over r cubed to the object, and then another 1 over r cubed back to the receiver. And that means a total geometric decay over 1 over r to the 6th. R to the 6th is a really big number.
Right. Your microphone isn't on.
Oh, oh, that's better. So 1 over r to the 6th. It's a really big number. So what would be nice, I mean, we're never going to get rid of this guy, right? Excite the target, 1 over r cubed to the receiver. We're hooped there. But, you know, suppose that instead of this guy, we actually could have, you know, a big transmitter. Like, just imagine a loop of wire that was, you know, a couple 100 kilometers on the side, sitting upright. And you basically got just a plane wave that's coming down, so there's no geometric decay. And then that would now mean you only have a 1 over r cubed roll on. So that's what we want. Of course, we can't do that. I mean, look, not even gap geophysics can build you a 100 kilometer, 500 kilometer loop and fly it. They won't do it, okay? I don't think.
No.
No, okay, just wanted to check. But we have natural sources. Here's a picture, not to scale, of course. Here's the sun, and here's our Earth. So Earth has got a magnetic dynamo field inside, kind of looks like a dipole on the large scale. And then we've got a magnetosphere around here. We've got this solar wind that comes out from the sun and sort of snakes around. It kind of blows the Earth's magnetic field backwards. And the result of all of that business is that we end up with aurora. So how many people here have seen, I guess, the southern lights? Oh,
Antarctica.
Antarctica, sweet. So, yeah. And anybody else? Yeah, there's a couple of people.
Northern Lights.
The Northern Lights, okay. So, yeah, we see them at the North Pole and at the South Pole, and if people have experienced that, they are absolutely stunning. I mean, you just get these sheets of light that shimmer. It's magnificent, and especially if you're in a snow environment. So if you can see it in wintertime, and then you've just got this, because everything lights up so much, and it's absolutely awe-inspiring. So they're really great. The other source is lightning. I mean, lightning is just, you got charges in the cloud, charges in here. Eventually, they get up, break down the electric field, and you get a current that's going through. Current, time-varying magnetic field. Good to go. Here's a movie. It's a short movie clip of how the aurora gets built. And what we're going to see is the sun. And as everybody knows, there's a lot of solar activity on the sun, and you get charged particles that spew out, and they erupt, and make their way to Earth. So there's the eruption. Particles going out. Now they're charged particles coming in, interact with the Earth's field. They kind of flow around. Now here's the amazing part. Watch carefully. Very carefully. Zingo! There's a field line reconnection. Brings all the charged particles in, and they funnel down the field lines to the north and south pole. And there is your aurora. That's where another movie, another shot.
Did it come in from the back of the on the far side? What's the meaning?
I don't know. I've never really understood how that field line reconnection works.
Yeah.
But that's what happens. They've got all kinds of satellites that monitor this. But yeah, the particles go around, and then somehow there's this field line reconnection. It traps those particles, whips them back in, and then they, then they funnel down the field lines, and then they just get guided to the North Pole and to the South Pole. Yeah, the magnetohydrodynamics of that, I think, are pretty non-trivial. Yeah. So the thing is with these, and when you get this big storm, there's a lot of current that's going, right? So you got time varying magnetic fields, because you've got all these time things are changing. So that means that if you're sitting any place on the Earth, you're going to see this electromagnetic induction happening, right? Time varying magnetic fields coming in. Any place on the Earth, you're going to get currents. Why you're particularly worried about things like these solar events is that these are really big storms. And if you imagine that you've got a power grid, so you've got all these connected wires, it's like a big loop. So you get this massive flux, magnetic flux that comes in. So that can induce voltages in your power system grid, and that can cause havoc with your whole power system. In the 1990s, there was a big power outage. Virtually all the east coast of the United States and Canada got wiped out for about 3 days. Because once these voltage surges start, if you can't shut them down quickly enough, that just goes through. And I've seen these movies of these these transformers. Like, it's just like firecrackers going off as this thing goes around, hundreds of kilometers, and they, you just can't. They couldn't stop it at that time. Electromagnetic induction, all the same stuff. But so the USGS, for instance, now has a pretty active program on geomagnetic hazards. So they also cause havoc with satellites too. So everything that is around that's got metal in or it has any kind of area that has got metallic around. It's subject to the same things that we talked about this morning. It's induced currents, causes a problem. So what's going on here? Let's look at lightning strikes from the MT viewpoint for the kinds of frequencies that we're interested in. Lightning is an important part. So it doesn't matter. In Australia, for instance, well, we did see lightning last night. But in the tropical equator climates, you got lots of lightning strikes. And then what happens? So you got this current that's coming down. So you got a very magnetic field, and it bounces up. You have something called the ionosphere. It's about 110 kilometers up. And at that point, the things are really conductive. So it looks like there's a conductive sheet up here, and the Earth itself is a big conductor compared to air. So if we have a lightning strike here, this thing operates just like a waveguide. It's kind of like the same deal that we had with the hydrocarbon layer. Remember how it went in and kind of channeled along? So that's what's happening here. It's kind of like a waveguide. It just sort of funnels around, and so it doesn't lose a lot of energy. And the result of that, we have a magnetic spectrum that looks like this. So this is power, this is period, and kind of goes up like this. There's a little bit of a notch in here that in practice causes some difficulties with collecting data. So this is a kind of interesting thing. People who've done waves, everybody knows about Snell's law. right? So if you're looking at a light wave, for instance, and it goes into a medium with a different refractive index, it changes the direction. That's why you see different colors in a prism. The same is true with electromagnetic waves. A wave is a wave. We talked about wave number. And so a wave comes in, so it's a plane wave that comes in. It's got some angle of incidence with respect to the normal. And then it's going to refract according to Snell's law and wave number. And the angle of transmission, theta t, is related to the angle of incidence, theta I, through this formula. But because of all of the values of the physical properties here, turns out that a wave, even a plane wave that's coming in at like 89 degrees, right, just gets refracted straight down. So as far as kind of thinking about how things are working in the Earth, you can generally think of magnetic tellurics as plane waves propagating in that vertical direction. The other thing that's important, of course, is what we talked about earlier, namely skin depths. So higher frequencies don't penetrate as deep. And really, because of how fast things are attenuating, these waves really only get in a fraction of a wavelength, right? You don't want to see a whole bunch of wavelengths. They just attenuate too much. So we talked about control sources. And when we talk about magnetic tellurics, there's a lot of things that are the same. First of all, we're going to measure the same fields, measure electric fields, put up 2 wires, measure magnetic fields. We do that for the magnetic tellurics. The difference is that in the control source, we know the source. We know its location, we know what's going on, we know when we put the pulse in, we've got all the geometry and the amplitude, and so we're good to go. In natural sources, we don't. We just got stuff that's coming in. Lightning strike here, something here, something there. So they're random in space, they're random in time. It's just a hodgepodge of magnetic field information that's coming in. You somehow have to decipher that. The good news is that if I look at Maxwell's equations, the electric and the magnetic fields depend the same way on the sources. Ultimately, what that means is that if instead of working with fields individually, I take a ratio of these fields, then all the effects of that source kind of cancels out. So that's the basic idea. Don't quite take a ratio, but it's kind of the same. It's called a transfer function. And basically what that does is tell you how, if I know the magnetic field, the horizontal components of the magnetic field, then I can use that with this transfer function, or it's called the impedance matrix. If I know this guy, I'll tell what the electric field is. So basically, a transfer function is just a way of like, okay, you tell me something about this field. I'm now going to have this relationship that tells me what this other field is going to be about. So this is an impedance function, and it's a relationship between E and H. So it's a 2x2 tensor, and the magnetic telluric station is going to be involved with collecting the EX and the E, Y, H, and different B fields, and these things are going to be connected through a transfer function. When we collect the magnetic telluric data, we're also going to collect generally a remote reference station where we collect the horizontal components of the magnetic field. I'll show you why in a second. There's a couple things that are important here to distinguish, because like I talked about a plane wave coming in, but there's a few subtleties that are really important, and it gives rise to 2 different modes that behave differently. One is the TE mode, which is the transverse electric mode, and that means that the electric field is parallel to the interface, the magnetic field. So that would go through like this. The other is something called the TM mode, where now the magnetic field is parallel to the interface. Well, at 4 o'clock in the afternoon, you're probably like, okay, so what, right? Who cares? But here's why you care. Because remember when we talked about this morning, we talked the importance of, where an electric field is compared to the boundary. If I have an electric field that's like this, it's now going to cross that boundary. That means that things are going to happen. Like I'm going to get charges that are going to be built up down there, and here I'm not. So they're two kind of different phenomena, so it easily broke up into two modes. For a homogeneous half space, I've got an impedance now just sort of EX upon HY, and that can be converted to an apparent resistivity. So again, we've got a formula to go from a measured number, the amplitude of the impedance, to a resistivity, and it's complex, our impedance, and it has a phase. And for homogeneous half space, that phase is pi by 4 factors. So in 1D, so here I've got a 1D Earth, 100, 10, 500. My impedance tensor actually is just got off-diagonal elements, and they're the same. And if I compute my impedance and convert that to apparent resistivity, I get a plot that looks like this. So what we're looking at here is period going this way. So this means I'm looking deeper. And here's our apparent resistivity. And you can see here, so it's doing exactly the kind of thing that you'd want at high frequencies or low periods. You're basically, skin depth is very close to the being shallow, so I'm getting 100 ohm meters. As my frequency decreases, I'm starting to see deeper, so I'm starting to see the effect of this 10 ohm meter, so it goes down a bit. Doesn't hit 10, but kind of gets down. And if it goes down, a lot more, I'm going to be sensitive mostly to this 500. You can see how it's propagating. So intuitively, in kind of 1D, it's behaving sort of what you think. Phase is a little bit different, but that's sort of the idea. So we have an app. You can explore what the apparent resistivities and phases are, change your Earth model, and just kind of get a sense relationship between the model and the data frequencies. In 2D, now we have to start thinking a little bit more about what's going on. In 2D, our impedance tensor still has diagonal elements, but the off-diagonal elements are not equal. And here's a case here where we're looking at the TE mode, because we're kind of parallel to this structure here. And if we looked at the electric field, it's going to actually be constant. So we're going to do a traverse this way. The electric field is this way. It's actually constant as we go. But the magnetic field changes like that. And if we looked at the apparent resistivity, it goes from 100 on this side, which is what we like, down to 10 on this side. So everything kind of, is copacetic. We look at the apparent resistivity curve. It actually makes some sort of sense. What's going to happen if we do a TM mode? So in a TM mode, this electric field is going to party this way. And we saw, oh, wait a minute. The electric field is pointing across. Current density has to be constant, but J is equal to sigma E. If sigma changes, E changes, so there's got to be a charge. And that's exactly what happens. The electric field comes across here. There's a discontinuity at that interface, which is caused because of the charges that are built up. The apparent resistivity is a bit crazy, right? It kind of looks like this. So more or less constant on the back end, but in this region here, it's really odd. So that's kind of what one's up against. Again, if you come to 3D, things are just complicated. Right? It's just very difficult to intuit. These elements here, the diagonal elements, are no longer zero. No special symmetries, nothing that's easily graspable on. So you kind of need to go immediately to numerical processing. Maybe it's just a couple of comments about the data, because it's kind of interesting. You're measuring data in time. Okay, so here's UX. This is 1 second, and you can see how much things are changing. You're measuring this in time, but you actually want things in terms of frequency. So immediately you think, oh, I'll take Fourier transform. But then, like, wait a minute, you've got something coming in from there, something else coming over from here. So there's a lot of stochastic stuff that's going on. And yeah, so you have to kind of figure out how to contend with all of that. So our typical stations are going to be like this with remote. And then the way that it's processed, and actually I'm hoping that maybe there's people in this room that are actually connected with magnetotellurics that would like to contribute or be part of open source community to kind of further develop the processing. This is really interesting. This is the key step in going from the measured data. You want to go to the impedances. And if you talk to anybody who's doing it, they say, oh yeah, that's trivial, we got some software, right? And then you say, well, how is that working if you wanted to change this? And they say, well, oh, I don't really know. Actually, it's really complicated. I looked at that software once and it's just really hard. So you get these kind of mixed things, but what everybody would like is actually to have something that they can look at, something that's open source and see, okay, this is how it's working. Now, maybe for my particular situation, I want to change this, and I can go ahead and do it. So unwrapping all of that, unraveling it, that's a goal. And we've got, actually, as we travel worldwide, that's been one of the things that really has resonated with people. So maybe there's somebody here that would be kind of interested in joining that conversation. So this is kind of how it's done. It's enough to kind of conceptualize. Take a time series, just divide it into a whole bunch of windows. For each window, take Fourier transform. So now you got a whole bunch. And then our impedance function is kind of like EX upon HY, but we're going to kind of take a cross correlation with this remote reference station that we got. And then we're going to do a lot of averaging. So we're going to do it now, average, and just keep going and going and going until statistically we actually have a good relationship between the electric and magnetic field at a particular location. When it comes to inverting, again, there's nothing particularly special about the MT, except that, yeah, you need to have a big enough grid so that you can handle the boundary conditions. That's the one thing that distinguishes it, because you could have something that's happening way off the coast of Australia, maybe channeling currents up through, some, lithospheric conduit, and actually affecting you on land. So it's kind of nice to. You need to know how to kind of handle it. But really, otherwise, magnetotelluric data is the same as any kind of control source EM data. So let me do one case history. Case history I'm going to show is from Iceland. So it's a geothermal. So Iceland is, sits on the mid-Atlantic ridge. So that's where the plates are going apart. And we've got lots of fumaroles, lava, stuff that's coming up here. Iceland gets a major portion of its electricity from these geothermal power areas. What's the typical geologic or geoelectric representation of this? It's kind of as follows, and this is sort of how it works. So first of all, imagine you've got a heat source coming in. So there's high concentration of magnets, might be pretty deep. And then we've got water that's coming in from the sides, and that's kind of hitting the stuff, circulating around. And then there's an alteration that occurs to give smectite clay up here. And the end result is that to first order, you get resistive near surface, get a conductive clay, a resistive core, and a high conductivity heat source. Okay. Usually in these empty earth, geothermal empty sites, what they're looking for, what they'd really like to do is get the bottom of this clay cap. So you can appreciate already from today, like, okay, that's a bit of a challenge. Getting the top is probably not so bad. Getting the top and the bottom might be a little bit more challenging. The other thing that is distinguishes this particular case history is that there's another layer of things that are happening. So we still have circulation up here. This is what we're looking for. But because of that circulation, high temperatures, this is actually a little bit lower resistivity. So at the end of the day, we've got this conductive top. We've got this host rock here. This might be a couple hundred to 1,000 millimeters. And then there's a reservoir in here that's actually a little bit lower resistivity. So not as low as this, but kind of intermediate. And this is the guy, if you can find him, is probably your sweet spot. So here's the survey, done with Phoenix equipment. Here's your coils for measuring T. Here's your electrodes for your E-fields, lots of wires. Remote reference, about 40 kilometers away. And we've got about 133 stations. We're just going to look at a couple. So here is station 1 and 3. Let's look at station 1 first. Here's the apparent resistivity. And you see a couple of things. First of all, the resistivity up here is about 100 ohm meters. The other thing that you really notice is that the red and the blue curves, so that's the TE and TM load, they're pretty much on top of each other, which is like, okay, that's quantity. These curves stay the same in the top region, but they decrease. So we're going from something that's really resistive to less resistive. And then, so you've got resistive, conductive. Now the curve split. Resistive, conductive, resistive. So just by looking at the apparent resistivity curve, you kind of get a sense of the gross feeling of what's going on. That there's there's a few layers, something interesting happening because the two modes are splitting. If you look at this region here, then there's something that's really quite different. First of all, the overall resistivity is much lower. It's about order of magnitude lower. And secondly, the red and the blue curves have split, so there's something interesting here. But it's still kind of resistive, conductive, but definitely different. So there's a lot of stuff happening between here and here. And also, in this region here, there was surface alteration with hot water and a few modes. So kind of, it's telling you something, right? You need to unravel all that. So we can do that. Take these 133 stations, all these different frequencies, look at the ZXY, the ZYX, and invert that. So they're just about 5 orders of magnitude in frequency. Do your big 3D volume. And now we've got a cube of conductivity. Here's one representation here. It's kind of interesting presentation. We've taken the cube and we've kind of sliced things out. So first of all, the red is conductive material, blue is resistive. But then there's also an isosurface that's generated to indicate the resistive core region. So this region here, which is kind of coming out, so you've got this cut, right? And then you've got this core region that's coming out. So here's that resistive core that we're looking for. And you see that there's this spot in here that has a low resistivity. If you just look and you just cut that straight across, then you're like this. So you've got this red conductive region, which will ultimately be the smectite core, and here will be your this is more resistive, and here's your kind of heat source. So that is, in fact, the interpretation that this is the clay cap. This whole region up here is basically your resistive core, but then there's a reservoir in here and in here that are making it less resistant. So all of that kind of corresponds very nicely with this. So here's our reservoir here. This stuff here is this resistive host. And then the bottom is your conductivity. So that's the interpretation. And in this particular case, there was some validation. They drilled a lot of wells. What we're seeing is color on these wells, and that indicates temperature. So these are high temperature values up here, which is kind of coincident with your reservoir. This guy coming in here is low temperature, which is kind of consistent with what we've got. And so we've got the two reservoirs kind of nicely, distinguished here with the empty. So I think this is a really nice example of the use of magnetic torques, and I think this is one of the nicest geothermal examples that I've seen. Okay. Anybody here use it? Yeah? Not very popular. Too much regular. Okay. Quickly going to any questions on MT? Okay, just give me GPR. And use polarization.
Just what you're getting at, I'm just going to pass out the.
Oh, please.
I'll just pass these around. If you guys don't mind filling them out, we certainly appreciate that.
Oh, yes, we really. The only thing we ask you to do, fill out the maps. But we are going to ask you to do some more. There's people who aren't going to be here, so you might as well fill the same time. Okay. That's fine. Okay, what's our motivation here? The motivation is that the electrical resistivity, as we've talked about it up to now, is that like if we took a chunk of rock and we assign it a particular resistivity, 47 ohms, right? However, you have to think about how this measurement is actually made. Usually it's put into a little circuit, and then there's a generator that is operating at a particular frequency, and then you're measuring current and voltage, and you're using that to calculate the resistivity of this thing. If I change the harmonic frequency at which I'm doing this measurement, sometimes the output resistivity changes. So in other words, the resistivity that I measure is a function of frequency. And here's what happens. At really low frequencies, the resistivity is high. And at higher frequencies, the resistivity is lower. So that's the real part. And the imaginary part is what this. So remember exactly, it's the same kind of thing, right? So I say real and imaginary, right? But there's nothing that's changed. I put on a harmonic current going in, I measure a harmonic current coming out, and sometimes there's a bit of a phase shift. So that phase shift allows me to say, okay, it's a real and imaginary. So this is exactly the same kind of thing that we had when we were doing frequency domain EM, right? So where is it important? Minerals? Permafrost, maybe. There is some potential application, groundwater, massive sulfides, maybe some geotechnical. There's a whole bunch of areas. So what I want to do is give you enough background so that you've got a kind of physical understanding of what's going on. Here's the idea. The concept of something being chargeable is as follows. So if material is not chargeable, so imagine the DC resistivity survey. So here's our current, like this. And if we measure the voltage, it'll look exactly like this. So let's do the next part. If the material is chargeable, we get this really interesting phenomenon, first kind of observed in just after the Second World War. The voltage initially rises, then it just keeps going. So it goes up, and then it just keeps going. And eventually it asymptotes. And when that first came about, people were like, excuse me, what is going on here? They didn't know what to call it, and so they called it overvoltage, because this number is gradually increasing. So in the early days of Newmont and Bell Labs, they looked really strong at that. And then they started to realize, like, wait a minute, this is really complicated. And it's things that are going on at a microscopic level, and really modeling this down at that micron level is really tough. But there is this macroscopic representation that we can grab a hold of. So there's a couple of ways of sort of thinking about this problem, and I think thinking about the problem is all we need to do, because if you have a mental construct in your mind about what is happening physically, you're pretty much done, right? Like that's what you need, because you can then translate that into something that's really meaningful to you. So here's where we're going to go with that. We're going to look at what's called membrane polarization. So you can imagine that you've got two pores. Now you're at microscopic scale, right? So we've got 2 grains of sand, and there's a little pore throat here. It's porous. There's some fluids. There's ions in here that are, so the whole thing is electrically neutral. Right? Start with. And now what you're going to do is you're going to take and you're going to apply an electric field. So how do you apply electric field? I mean, we've already seen how we can do that. You can imagine also that you just kind of hook a battery up, right? You, like if I have a positive terminal of battery here and a negative terminal of battery there, now I've got an electric field that's going across. Okay, so what's that going to do? Well, if I have a big positive charge here, then all the positive ions, are going to want to try to get repelled, right? They're going to try to go this way. The negative ions are going to try to come this way. So you can see that when I apply this electric field, that is the state that I'm going to want to build up. But I clearly can't keep that going forever, because if I start to have too many positive charges in here, the next positive charge sees the repulsion from here, but also sees the repulsion from here, and so eventually I'm going to asymptote out. Okay. So that's it. So that's the essence of how you can think about this problem. Got a neutral state, apply an electric field, charges want to kind of move, they get bound up with some kind of boundary or pore throat, they gradually build up to some asymptotic level, and then you're ending up with an accumulation of positive charges here and negative charges there. So that's a good way to think about things, because it allows you to do a whole bunch of sort of intuitive understanding. Before we talk about that, there's just a couple of diagrams to show you which materials are chargeable. So there's some that, like pyrite is pretty chargeable, graphite, and others are less so. And also with different soils and rocks, a whole variety. The big kid on the block are sulfides. They have huge chargeabilities. So if we come back to our voltage build up here. So here's our conceptual model of what's going on. And now we've got here this input current, and we look at the voltage, and the voltage initially rises. Now it keeps coming up. So you can now you can kind of visualize like what's going on, right? So initially there'd be a lot of charges, quickly build up, and then gradually asymptote. Now you're steady state. And then you turn that forcing off, drops down, and then those charges decay. The way to think about this theoretically was introduced by Siegel, introduced the chargeability, which is a scalar value between 0 and 1. And usually for most of the chargeable materials that we deal with, for mineral rocks especially, chargeabilities of 0.1 or something is fairly representative. So the theoretical chargeability is actually the ratio of this guy here. So the moment you turn it on, it drops down to this. And then it's the ratio of this guy to this guy here. So it's given by that particular formula here. It's a useful mathematical definition. We can't measure that because there's just, first of all, you're trying to turn things off. There's no way you can get things right at the turn off, and also you're going to have all kinds of induction stuff, so can't measure that. But what you can measure is anything that's associated with this decay curve. And that's really the ticket. So anything, this is a secondary field. It's caused by those charge buildup. Anything that you measure that's somehow representative of that, it's good to go. You can call it chargeability. So it could be the value of this potential at a particular time. It could be the integral. This is what people used to use. Use the integral under that curve over a couple of time windows. All things are possible. Also in the frequency domain, you can do multiple high frequency, low frequency, and look at the difference. Or again, we can go back to this phase shift, put in a look at the difference in the voltage phase compared to the input phase, and use that phase. Usually that's in milliradians, and that's also an indicator. The importance of chargeability being small means that the effective chargeability, or effective conductivity when something's chargeable, takes this kind of a relationship here. But if eta is small, then anytime somebody says eta is small, you think, Taylor expansion, expand things out. And so we could do that here, and the result is that it allows us to write any IP data as a sensitivity matrix times the chargeability, where this chargeability has the same units as this. So this could be in the time domain, so it could be millivolts, it could be millivolts per volt, it could be milliseconds. These are your data, that takes the same units. And this J, the sensitivity, that tells you how the electric potentials change with the change in conductivity. And we really get that by solving the DC resistivity problem. So kind of a summary of the data, we can work either in the time domain, the frequency domain. We've got this kind of a linear relationship. J is just some matrix of sensitivities. And this chargeability that we get out, which we often call pseudo-chargeability, is the same units as the data. So now we come back to things that we saw earlier this morning, and this is different. So in here, the conductivity is constant. The only thing that's changing is this block is now chargeable. So we're going to do this IP experiment. Got that as a pseudo-section. Same thing this morning, drilled here, you're okay. Now we put little bits of clay, graphite, chargeable stuff up here. And again, we have that same kind of marked pseudo-section. Can't tell anything from that. And here's our GIF model. Again, constant conductivity, but different chargeabilities. And there's your chargeability pseudo-section. So you're collecting, I mean, it's sort of continually paralleling the DC resistivity data, except that you're actually using a different number, but you're plotting it in the same way. So the inversion now is a bit different. So how do we do? We collect the DCIP data, and we're going to invert those potentials to calculate the conductivity. Okay, that's the DC resistivity problem. That's where we were this morning. What we're going to do now is we're going to take this conductivity, we're going to use that to compute the sensitivities of data to a change in conductivity. So it's going to give us our mapping that we're going to need for modeling the chargeability data. And now we've got that, we can go ahead and invert for chargeability. Okay, so it's a two-step process. The first step is always to invert. We need to get this background conductivity. Once we got the conductivity, then we invert, calculate this sensitivity function, and we invert that with just kind of like a magnetics or gravity, just a linear problem, and get out the chargeability. So my skill testing question for 4:36 in the afternoon is, who recognizes these plots? For Paula Capsagnan, Shiraz.
Can you give us a hint, though?
Well, people met. I was sitting out in coffee, and we were just kind of talking about capturing successes in our case histories, and then also capturing failures in case histories, so because we could learn from failures. And people started mentioning particular deposits, and this was one of them. Pardon me? What have people done?
Are we seeing it today?
No, brand new. But somebody mentioned it.
You didn't mention it.
Long Hue? Pardon me? Long Hue? No.
Century.
Century! Who's the Century?
What you said.
Sweet. Okay, Century. So this was actually one of the first DCIP data sets that we used. So this was Bob Smith at CRAE, and he gave us these data. It was a Century deposit. We inverted, got the conductivity out that looked like this. Basically, there's an overburden up here that is varying. There's some faults in here. The mineralized zone is like this. So conductivity does not tell you the story at all about mineralization. However, if you take this conductivity and you compute the sensitivity, invert chargeability, you get this. And this was actually astounding. I mean, this was one of the first times these DCIP data had been inverted, and the results were actually really quite remarkable. Right? So we've got, here's the mineralized zone here and here. There's this fault that's coming in. Right. So if we apply that to our test examples here, here's our chargeability model. We get something that looks like this. So nicely delineated. Again, it's round because we're asking for a smooth model. Here's our prism with a lot of clay and graphite, pseudosection, uninterpretable, inversion, exactly parallel in BC, right? And not only do we see the chargeable body here, but we got the little bits of junk up there, which might or might not be useful to. And then here's our GIF model. Again, drilling here, we put on here, and you unravel it. It looks like that. So now we're all set up. We can go back to what we started with this morning. We're going to go back to mathematics. So this is, well, actually the initial paper was for an ASCG publication for a conference. So it's an extended abstract. That's as far as this guy got, was Andrea Rutley. And her name?
It's ASCG president.
Right now.
Yeah.
Right now.
Yeah. Right. Correct. Same. So, you've kind of seen this before. So here's our setup. So I've changed the question. So can a conductive chargeable unit which would be potential targets within siltstone, be identified with DCIP. So now we're starting to get a little bit more clear on what it is we're actually looking for. So now if we look at our rock units, so we've got conductivity. Remember the thing that was really distinctive was this black shale, breakaway shale unit, had a very high conductivity, but for chargeability, it has maybe low to none. I think there's still some reason to debate this, but I think that's basically it. But the guy that we're looking for, this Mount Nova Horizon, has a high conductivity, not as high as the breakaway shale, but it's got a high chargeability. And that distinguishes itself from from the volcanics and from the other siltstones. So there is a potential here for actually being able to get this. So just to recap the synthesis from the DC resistivity, if you remember this morning, we ended up with this long conductor here. That was the major unit. That was that black shale. And then we had a little bit of a moderate high conductor in here. And we were suspicious of this as being maybe that's part of the Mount Nova Horizon. So now we're going to do the same thing as we did before. We had pole, dipole, pole data. So we had the pseudosections. We're going to use the same data. Notice that these pseudosections are cut off. And when we did the DC resistivity, it went down. We cut these off. Any idea why they should be? Why anybody would cut them off?
Too noisy.
Exactly. Yeah. So remember, IP, it's a secondary signal, right? So you're already looking at a secondary signal. If you have a really, really long offset between your transmitter and receiver, those signals are really small. And so we just couldn't do anything more than kind of get to, I mean, that is still n equal 10. Not bad. So now we do the same thing. We're going to invert those data. But remember how we're doing this. So first of all, we have to get the conductivity from the DC resistivity. And in this case, it's important actually to do that because we've got this great big, conductive shale unit that's coming through. And we want somehow we need to take that into account. So we take that model and generate the sensitivities and then do the inversion. So now we still have this 3D cube, and we're going to see exactly the same things we had before. So here's a 3D cube of chargeability, and we're going to slice in, down, and spin around. Back. Look how different that is. So look at the guy on the left. See the chargeability? Right. Down. Around. Remember, now we're only going to be left with the highest chargeabilities. Yeah. So what's distinctive here is this unit that is coming out here. This is pretty mucky. I mean, there's a lot of kind of chargeability stuff that's going in, but I'll show you on the next slide how things really work here. So here's the resistivity model. So here's that shale. And here is what we're going to now define as being the E horizon. That's Mount Nova. If you overlay that chargeability, the chargeability on this, here's that Mount Nova horizon. This black line is the black shale. So through most of it, there's no connection of this unit being chargeable and back here. There is. I don't know. There's some stuff here. I really don't know what it is, but I mean, there's no reason to believe it's kind of related to the black shale. So there's just some other stuff that's going on there. I don't believe that's mineralized. And it doesn't coincide with being highly conductive and chargeable. So the thing that's highly conductive and chargeable is this region in here, and then this region in here for me is chargeable. So I think like this is a great example, and yeah, as I said, I'm very proud of it because it was like one of the first 3D DCIP examples that was done. And interestingly enough, when we did initially, we couldn't use nearly the number of cells. And the one thing about having poor resolution is that the story was a little bit simpler, right? Because you just looked at the plots, and these things kind of came out even more simple, and there wasn't stuff that was happening here. But now, as we kind of refine things a bit more, have smaller cells, you're actually picking out more information. There's another part of the case history that I think people might find interesting, and that is when we did the inversion this last time, there was actually kind of a conductive anomaly that was sort of sitting out here, just a little bit off. And then we did some hypothesis testing and tried to put in some geologic constraints, and we basically came to the conclusion that doesn't happen either. So I think it was kind of a nice, rounding out of the story. But one of the things I'm hoping yet to do on this trip to Australia is to make sure that we've actually got this story right. And you saw today, Lindsay was showing you how easy it is to, make some comments on GitHub and on our EMG side, looking for Terry Harvey and other people to kind of get on board and see what we wrote and see if it actually passes.
So you created a very nice 3D looking model with just a series of pole dipole lines. Yeah. How much do you think you'd improve upon that using these 3D arrays now that people run around with?
Oh dear,
that's improve a lot, or 10% or 20%?
Oh, that's a hard question. I guess this is kind of 2D, and we actually put a little of that information into the inversion. In that, okay, we're kind of inverting everything in 3D, but we've got to preferentially align things in the north-south. So there's a little weighting there on the model. Yeah, I would want to have to. Yeah, so I think that was basically it. Okay, that's it. I do have some examples. I'm not going to show them, but do people know that if you're looking for a landfill, that using IP is a more robust and diagnostic indicator of a landfill than trying to look for low resistivities? For a landfill. It's a big deal in Europe. Actually, it's kind of a big deal in some places in the States too.
I've looked at the landfill with an EM34 that mapped it nicely.
Yeah, so there are some landfills that, because you get metallic debris, and so it can be
leachates.
Come up as conductive. Well, the leachate. So this is interesting. So the leachate is usually non-chargeable, right? So that's conductive, and actually the example that we have here actually distinguishes between the landfill's junk, okay, that turns out to be chargeable, and the conductive leachate, which is, there's nothing to be dug up. It's just, contaminated water.
In this case, the leachate was the problem, but it was seeping into the local creeks.
Yeah.
Now, you say the debris, is that they like metal boxes, or is it just the soil in the landfill that's...
Yeah, actually, so this was interesting to us because it could be construction debris. Some of that, like wallboard, things like that, actually seems to have a bit of a chargeability to it. And so that comes up as a resistor. If you have metallic debris, then that comes up as a conductor. But there's some indication even that green waste has got a potentially low background chargeability. So that's kind of that. be, okay. You guys still hanging in? Long day? Okay. We do it. The future. Okay, so what we covered? That's it, long day. DC resistivity, that, we're all about charges, EM induction, we learned something about the fundamentals, inductive sources in the frequency, time domain sources, we looked at mapping paleo channels, water present, Telexam, which never got to Magdalena, but it's there. And UXO, Steve Billings is going to be here tomorrow. He's going to talk about using time domain EM for finding UXO. And actually, if you don't like to think about UXO, you can kind of think about, massive sulfide deposit, because some of the things kind of come out about the same if you're working at long times and being far away, so that the responses can be linked back. Grounded sources, we did methane hydrates. We did the mapping sediments beneath the salt. Natural sources, we did magnetotellurics, GPR. Minerals, induced polarization, we did minerals, and yeah, did correct examples. Okay, where do we go? If I kind of go full circle here, I think we can see that we've actually got a lot of stuff going for us. There's a huge number of problems that exist. High quality data, lots of emerging capabilities, tools to communicate, and so I think we can kind of put all that together. So there's some sort of major issues here. Monitoring is going to be huge, whether it's for aquifers, enhanced oil recovery, hydraulic fracking, CO2 sequestration, or coal seam gas. All of these things could benefit because there's changes in the electrical conductivity with what's happening. Then having sensors out there that are sort of permanently monitoring things can be really, really valuable. I mentioned this within the context of the SIL code. I mentioned steel casing. I just want to elaborate a bit on that because it's just got a whole bunch of tentacles here that are kind of interesting. They're also really shows why there's still challenges left in this game. But here's the idea. So we talked about excitation, right? So suppose I've got a body down here that I'm trying to detect. So maybe I'm injecting CO2 in here or something else. And I want to detect that. So it's a resistor, okay? Right. So we don't want to use an EM technique, right? We want to kind of make, well, we don't want to use an inductive source. We want to use grounded source. And we've got to get energy into there, right? So if I just have my grounded source on the surface, it's hard to get stuff. But if I had a conductor, like just a big rod that I could put down right next to here, then I could just light this guy out. So that gets my current injected into the ground, and that might help me out hugely. So this is what the oil companies have discovered. It's like, wait a minute, we've got some hydrocarbons here at depth. Maybe it's an oil field that we thought was drilled out, but we don't really know for sure. And it'd be nice to kind of test it and see what we can see. So maybe if we used kind of like a DC resistivity experiment and then had current that was coming down into this target zone, we might actually be able to build up current charges here that we could measure. Okay, good idea. What are we up against in practice? Well, in what I've seen in drill casing, they're like 10, 15 centimeters in diameter. And the outside of this, so this is maybe an example of drill casing, outside is maybe a centimeter. the electrical conductivity of this thing is like 10 to the 6th Siemens per meter. It's also highly permeable, maybe mu naught or mu is like 50 to a couple hundred. And it's very long, just a couple of kilometers. Now you start thinking, oh, wait a minute, this could be challenging, right? Because now I need to have cells that are a fraction of this. So let's say a quarter of a centimeter. This is 2 kilometers. I've got 10 to the 6 contrast here to my background. And I've got different scales. This guy down here might be 100 meters. I mean, it's just, you know, it's just kind of gets tough. So there's lots of different scales, lots of variables in terms of geometry and size, as well as in the physical properties. And really what you want to do is to understand how these currents are doing. So you might put a generator, attach it up to here. So the currents are going to go down, but then they're also going to emanate out from the side. And you know, you want to know how those guys are, because if you've got something out here, then it's going to interact with that. So yeah, things like that, and then things can get a little bit more complicated because you put pipes down there, they corrode. So now you've got something like this. Well, that's not going to pass electricity the same way as the other. Lots of problems, but people are working on it. And you know, the kinds of things that are interesting. So here's an example. We've got a casing well here. It's going into some of your hydraulic fracking down here. So maybe some fracking fluid. We've got another well here. So you want to model all these things and kind of find out what's happening. And sometimes things just get a little complicated because you haven't even taken care of the details. So this is a typical well pad that is used, and you can imagine putting a generator on here and then driving the currents down, right? So that seems like a no-brainer. But if you had a single wire that was connecting here to maybe some storage shed, and you look at the potential, you see that you've not only lit up this guy, but you've also lit up the shed over there. It's just completely unintentional, just a little wire that's connecting these guys, and it's not changed the whole thing. So I think the point about that is that it's tough, and you got to take care of the details, but if we do it, we might be able to get at something that's really interesting. The other thing is, people ask you like, okay, can you use EM to help solve this problem, right? And it's just like the tunnel thing, right? Well, I don't know, what exactly are you asking? And sometimes it's different. You should be asking different questions, and you should be using different EM techniques to answer that particular question. Here's an example of where it's for something called SAGD, steep assisted gravity drainage. And what it is there's a layer of bitumen, it's called heavy oil, and you can't pump it out very easily. So what you do is you put in a horizontal well, and then you put steam in that well, and that steam injects out, and it reduces the viscosity of the bitumen, which then flows down, and you pick it up with a well underneath. So that's an application. And what you'd really like to know is, okay, where should I slot these things? If you're going to develop a field, where do I put it? And then how do I monitor things? And there's a whole sequence of things. So I'm just going to take you through. So stage one, just to kind of look at things, you might do a reconnaissance survey, and maybe you're going to do stage two for pre-injection, maybe surface borehole, and then you're going to have a monitoring. This particular image really set a few people in Imperial Oil kind of back on their tracks a bit. Because I'm going to explain the following. Here's the geology is, the basic geology is kind of simple. There's a an underlying layer here on this scale of the bitumen, and there's a region in here which is got a conductive cap to it, and this interface is called the top of the McMurray, and really that's what people are interested in. So you want to get through this conductive cap and see where this guy is here. What you're looking at here is the result of inversion of airborne data. So it's a VTEM data set that was inverted. And here's the assessment from the inversion of both the top and the bottom of that plate cap. And so of importance is this elevation here. And these are 3 lines, one across here. Okay, so the oil companies have been for years just drilling. Each of these little black dots here is a drill hole. So there's a couple hundred. And with that, they were able to composite what this elevation to this top of the McMurray is, and that's plotted in here. So this is the result of the interpolation of all the boreholes. Do the airborne EM, do the inversion, and you get this image here. Everything is on the same scale. And you can see the kind of remarkable correspondence between these two guys. So from the point of view of getting information out, sometimes these reconnaissance surveys can be actually remarkably effective. And in this case, they were. Okay, so now we've maybe stoked out our area that we're interested in. So now we want to kind of find the electrical conductivity of this region. So we're going to do a pre-injection, trying to figure out what the resistivity is. Because if you're going to inject something, whether it's CO2 or whether it's steam or something, you're talking time lapse here. So you want to know what is happening before you do anything, and then how things progress as a function of time. So that's that monitoring. So we're going to use, first of all, maybe this helicopter data, and then we might use some ground data, maybe a controlled source loop or something, and measure some data. So that would be fine. And then the next stage might be to maybe use some borehole data, which interestingly is easy to acquire in these cases because they're mandated to have observation wells every so often. So that would help you. That's sort of a different question, because now what you're trying to do is to find the background conductivity before you do any injection. The next step will be monitoring. And this was the image that really kind of, again, kind of set people on their heels. They were not expecting this. Let me explain what we're looking at. So there's these horizontal tunnels, horizontal wells that are going in, right? And then each of them, they're injecting steam. And so the steam is coming out. So it's like a well that's coming in here, injecting steam. And then what we're seeing is the steam chamber, going all the way up to the cap rock. And similarly here and here. So here's the 3 steam chambers. The interesting part is that this one here is kind of blocked. So in this particular section, the steam only has had a chance to get up to this side. So this is the synthetic of what's there. And now the done with this. So there's a large loop, enough to you need moment, right? Get some moment through there. There's actually 2 loops because you want to merge things from different angles. And then there's a number of locations in here that already would have observation wells. So these are just vertical wells. And then what was done is to say, look, those wells exist, so there is no substantial cost in just saying, let's put in a vertical electric measurement. So just instrument each of those wells. So no big extra cost in doing that over what has already been done. And so this is time domain EM data, inverted, and you get something that looks like this. What we've seen, so you can see the steam chambers, and not only that, you actually see the blockage. This result is great. So here's the mandated wells that are here. There's the result. What they do at this time is use seismic. It's very expensive, costs them a lot of bucks to do it. But also, it's not quite the right geometry because these things are like 400 meters below the surface, and that's a bit shallow. Because a lot of the things that they do with seismic, they're challenged by the closer stuff is to the surface, more difficult that can be. So I think this bodes well. It's great. I mean, supplied to SAGD, but this is imaging. So if you're looking for steam chambers or CO2, this has some potential. Marine EM, we've not concentrated on it very much, but there's methane hydrates that are important from Australia's viewpoint. There's a region around here that you actually have a lot of methane hydrate, so it's possible. But basically on that circum-Pacific belt, there's lots of places that there's hydrate, and the Japanese, I said, are certainly very big on this. C4 massive sulfides, this is again something that Japanese, Koreans, and other countries too. I don't know whether, is this something that has come up in Australian terms? Are you going to talk about C4 massive sulfides? So you get these big smokers that come up. And so you got water that's circulating through here and kind of goes up, and then all these sulfides, minerals kind of deposit. So incredibly rich. And then you can imagine, 15, 20 meters of this stuff that's sitting there. And the logistics, even if it's a couple of kilometers down, of putting equipment on the ocean floor, grinding it up, sucking it up to a boat, and the oil industry's got all that stuff down pat. So it's not a technological challenge, but where people are right now, and I think you'll probably see the Japanese into production on things like that within a year or two. Tectonic studies, natural hazards. So we've got all these plates going down, and imaging the conductive parts of these plates. Something I haven't talked about is anisotropy. In this case here, what we're looking at is kind of the ratio of the X to the Y resistivity values. So X being perpendicular to the ridge and Y being parallel. And there's a region in here where there's a large amount of anisotropy, which is telling you something about the dynamics of what's going on. Large scale, MT in particular. So you've got OSLAMP here. Anybody in this room connected with OSLAMP? Yeah, okay, maybe we can talk about it tomorrow. Anyway, so these are the sites that have been looked at. Here's the United States, similar thing. And actually one of the drivers for this guy is the geomagnetic hazards. Because if they can characterize what the electrical conductivity is, then they can simulate these magnetic storms, and they can find out how much, what electric fields they need to deal with in their power grids. So that's actually one of that's a driving force here for, in addition to sort of academic studies. Water, huge issue everywhere. Doesn't matter where we go. Finding it, delineating it, monitoring aquifers, managing it, saltwater intrusions, pollutants, just incredibly important. This is an example from California. Something else that's progressively important is data integration and multi-physics. This is a case history. I can talk about it a little bit tomorrow if people are interested, but it's basically kimberlite deposit. So kimberlite looks like this. It's sort of an explosive event. Diamonds stable at 120 kilometers. You get ejected out, and you end up with a structure that looks like this, kind of like a tooth. And there's different units here that have different importance in diamond exploration. But this has got a signature that involves density, magnetic susceptibility, electrical conductivity. And so these are a number of surveys that were done over an area in northern Canada. I'm actually particularly pleased and proud of this following result. This has just been completed by all these great students at UBC, where we, over close to a 2-year project, inverted both the gravity to get density, magnetic for susceptibility, frequency and time domain to get conductivity, and here's the new one, chargeability, with an inductive source. So this is airborne time domain data that's been decomposed to calculate the early and the late time chargeability data, inverted in 3D to give us effectively 2 other physical property models. So all of those have been done. It's just been published in a 3-part series in interpretation and geophysics. And the thing that's kind of cool about it is that by having all these different properties, you can find something that's conductive, not susceptible, very dense. You can just pick out unit identifiers and generate rock units from geophysics. So each of these little units here, rock 1 to rock 5, has got a different sort of sequence of physical properties. We compare that, which is taken totally from airborne data. No ground data in here, just totally airborne. And compare that with the rock model obtained from geology, from drilling. And there's really impressive correspondences. So I think this is again kind of where we want to go, right? We try to get not only invert for conductivity, we want to invert for others, try to find particular combinations of these and say, that's an identifiable rock unit. Use that. Modeling and inversion is all of the things that we've talked about today: high performance computing, collaborative development, open source. These things are all kind of coming together, and you can just feel that whole field just grow and people getting traction. The SIMPEG group has been, I think, admirable in that regard, and all of this material, this is stuff that Lindsay's going to talk about tomorrow, but it just allows people to do forward modeling, inversion of various kinds of data, and the more people that kind of can benefit from this and themselves contribute, the better off the community will be. So we'll talk about that tomorrow. With respect to modeling inversion, then there's also this interactive computing and visualization. So we talked a lot about apps, right? Those things are amazing. They just tell you. Pictures are so informative. Equations are one thing, but a picture and having some way of playing the things is quite another. And everything that we've done up to this point has all been developed in SIMPEG. It's all available. And then collaboration. This is kind of where we're going. It's all, everything we've done is on the web. It's there. Nobody's got copyright. You can view it. You can look at it. You can add to it, which is really what we want. We want to have people interacting. We want your case histories too. Things that make an impact in a positive way. Like here showcase the usefulness of MT. And as we were talking about at lunch, maybe if there's room for highlighting the failures. Maybe we could put a more positive word on that. But that's where we learn from, right? Try something, it doesn't work. Okay, if that's made known, then maybe the next guy is not going to repeat the mistake. So that's our goal. So that was it. That was the goals for the disc. Trying to inspire you. Maybe. Hopefully we've done that. Basically, with the number of applications, and you can see just how extensive EM can be used. We only touched the tip of the iceberg. There's a lot more problems out there to which EM can be used. And we've illustrated the effectiveness with case histories. Build a foundation. What's the basic principles of EM? And I can't stress enough the importance of understanding the principles. There's a lot of people that I've talked to over the years, they say, oh yeah, well, we did that in the first year, whatever, and then they go along and then they do something that is really silly, right? And it's just like, hello, just think about what it is you're trying to do. And then a lot of that's just embodied in some of the principles, and as you saw today, those principles can get scaled over to systems of different sizes and different frequency bands, but it's all the same. The apps, as I said, and our open source resource, GeoSci, is there to help build a foundation. I want to set realistic expectations. Hopefully we've done that. Gives you an idea a little bit about the diffusive stuff with respect to EM, and promote that community, which we're going to try to continue to do. So our resources, we've got GeoSci.xyz. So Lindy talked just briefly about this. So there's our GPG, here's our EM GeoSci, here's SimPeg, here's the disk, case histories, and this list could go on. So all of the apps are available through here. And lastly, I just want to reiterate that this has been a huge effort. It's a huge team. In addition to Lindsay and Sagi, who are both co-presenting with me over this year, there's a lot of other people connected with the development of this material, and a lot of other pictures that aren't on here. So I want you to join us tomorrow. Okay, so this is supposed to be a 2-day event, and it is. So tomorrow morning, what I'd like to do if people are interested, I think the topic that is of most interest to this group is EM decoupling. So I'd just like to talk a little bit about that because we've done a lot of work, and I think we have something interesting to say. We'd also very much like to hear what your case histories are or what your problems are, and just to get some sort of a feeling. So it doesn't need to be long. In fact, we don't want it to be long. But if we could get people to articulate what they're doing, where EM plays a role in 3 or 5 slides and a 5-minute kind of lightning talk, we could capture that if you're willing to share that. And that would give us and everybody else an idea of like, okay, what's going on in Brisbane? And I think that would be just valuable for everybody. It opens up communication. Somebody else sees like, oh, you're working on this problem. I've been doing something on this. Let's talk. So I know there's can I have a show of hands? How many people would be willing to, spend 5 minutes talking about what they're working on tomorrow? Up, way hands, way up. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. That's not bad. Okay, so maybe other people can change their mind over the course of the evening if you want. And we don't want a long discourse because we don't have time. But just something kind of short and sweet. Here's what I'm doing, and maybe if you've got a problem that's associated with it, that's even better. So here's what I'm doing. I'm kind of hung up here, or this is what I want to do. Can this work? We were talking in Denver, our very first one, we were talking with people who are just really interested in tunneling and things like that. And it was kind of cool. You sit around and you don't necessarily know the answers, but at least you start the topic of conversation and kind of continue. Yeah. So that's right. I hope you can join us tomorrow at what we call Disc Lab. And actually after we have the presentations from people, then there's a number of things that we can do, and it depends a little bit on what people like. We talk about SimPeg, which we'll definitely have some aspect of that. We could open up some apps, talk about that. We can also talk about how to program in Python and to yeah, just interact with code. So all of those things are possible, and kind of depending on what people would like, because we also have a ton of tutorial information about all kinds of things, so we got lots to talk about. That's it, guys. Thank you.
We'll start tomorrow at 9 a.m.
Yes. Nice. We're done with me.
Yeah.
Oh, I see.
Yeah, well, I'm yeah, I'm happy.
The other thing I was
Thanks, Lindsay. Thank you. Those ones are just like one day. You know, that is, yeah, so that's a good place to start. I can give you sort of the quick.